probability that the virus survives there without its protective cover is very low. So it's good to have hydrophilic surfaces. That was the takeaway from this particular paper that they had given. What is the current situation with therapy? People are trying for vaccination, they're trying for drugs, they're trying for herd immunity, but we know that none of them are really out there. So right now, prevention is the better option and possibly the only option many of us have in reality. Masks reduce airborne transmission. And this has been proved many times that if you wear a mask, the mask is going to stop the number of particles that actually enter into you, hence reducing the probability of you catching the infection. Because one or two viral particles are not going to really cause a disease. You need something called minimal viral load, which I'm not a biologist, so I will not go into this, but basically you need a minimum number of viral particles to enter into your system for you to be affected. So if you wear a mask, you're going to be protected from these particles. So if both people who are speaking wear masks, you have a very minimal transmission. If both are not wearing, it's a very high transmission. So the need for a mask cannot be overemphasized. And the second thing is like, it is not just coughing and sneezing, just talking, and especially talking in loud voices, which many of us are very, very used to, can cause the particles to come out. So even the act of talking, causes these particles to be airborne. So do not assume that a person who's not sneezing or coughing is safe. Nobody is safe. Just by the act of breathing or keeping your mouth open, of talking, you're going to be releasing these particles into the air. There is this whole story about what kind of a mask. You have the N95, you have a surgical mask, you have a cloth mask. Very briefly, just for those who are interested, an N95 mask filters the 0.3 micron particles, whereas a surgical mask actually filters the 3 micron particles. And the surgical mask is supposed to just be a protection of when you sneeze or when you cough. So it allows you to breathe from the sides, and N95 is very snug. It can make breathing difficult, but it's very, very efficient. Right. Then you have a mask with a valve. The valve is supposed to allow breathing out to be easy, whereas breathing in is difficult. It is okay. It is as good as a cloth mask, but definitely not as good as the other two masks, the N95 or the surgical mask. A cloth mask for most purpose is good. And not wearing a mask is not acceptable. I'm not wearing a mask today because I'm the only one here. But if there is a second person, immediately I will wear my mask, which is just lying around here. Right. I strongly urge you to go and see this particular YouTube video, which is by Professor Arnav Bhattacharya on PIFR, as a part of the INSICO with the group of scientists that I was talking about. He discusses masks in detail and the experiments that they have done. For what I've given are the conclusions that I've taken from this talk. But to know more, I would strongly urge you to go and see this particular video. Now, those are for the airborne drops. If the drops settle on a surface, what do? You use a surfactant. You use a soap. What the soap does is very simple. The surfactant nature of it, which means it has a hydrophilic and a hydrophobic end, they go and break these spikes which are there on the virus, and they pull away the spikes, and the rest of the molecules pull away whatever is left. So they actually break down the virus and kill it. It's called a coronavirus because it has a surface, and if the corona is broken, it can no longer survive, so it is safe. But because this is a mechanical action, like it has to go and actually split things, you need to give those 20 seconds or 30 seconds for the system to work. Just putting a soap and doing this is not going to work. You have to allow the surfactants to work. This is a highly efficient way of controlling. And that's about what I have done. I'm just going to quickly, the next 2 slides, I'm going to stop. This is just to tell you that my actual research, which I have not presented here, falls into these basic categories. Long back with Day1, we have worked on self-cleaning surfaces. Recently, we've been working a lot on self-assembly of liquid droplets with my scholar University, who's now a postdoc at NIT Trichy. We are also looking at droplet drawing patterns of complex colloidal systems, especially with reference to colors, Ashwini and Swati. And we're seeing if we can use artificial intelligence like deep learning machine to understand these pictures, and Saban is working with us on that. Those are about drops and droplets. And non-droplet work, I work a lot with liquids. So my papers related to liquids and about binary liquids, and we do molecular dynamic studies, stages and are and right from my PhD days, I've been doing a lot of ab initio, hard pocket PhD studies, and currently unpublished. These are a few of my papers, recent meaning the last 6 months papers. Just to tell you that this is what gives me the interest and the reason to be in today's talk. Thank you very much. And thank the organizers, especially Amit, for this particular opportunity to be talking to all of you. And my special thanks to this entire group of insightful the Indian scientist response to COVID, because I think I learned a lot from the group. I would strongly urge you to go to this particular site. It has a lot of information about what it is and what can be done, and there are a lot of resource materials, and these are all peer reviewed by scientists. I strongly urge you to go and check it out.
Thank you, Professor Madhurima, for making a very informative and excellent presentation and very relevant presentation. Specifically, presented the inside story of the droplet behind it. Now I'll request the participants to interact or any queries. 5 minutes is allotted for that.
Hello, Dr. Madhurima. Can I ask Dr. Madhurima a question?
Yeah, can you introduce yourself, because I can't see?
Yeah. Actually, I'm Dr. Jaydeep Bhattacharya from Kurseong College. Though I'm not from physics, I'm from literature background.
Yes,
Just
sir.
I have a simple query to make.
Yes, sir.
Yeah, actually, I've heard through your presentation. It's very nice and very clear to all of us who is actually not from science or physics background. Just I'd like to know that since you are talking about COVID-19 and all other things related to it, is there any difference between the effectiveness, against COVID, if we talk about isopropyl alcohol and ethyl alcohol? Is there any difference between?
Yes, there is a difference, and I would urge you to listen to that talk on masks by the TFR professor, because I think that is where I heard that the efficacy of, I think, ethanol is greater than isopropyl alcohol. There is a difference in the efficacy, yes.
Okay, ma'am.
And okay, from a very simple point of view, I don't know if you noticed the last slide, but when we look at the contact angle made by, two different alcohols, the contact angle, the drop shape is not the same. So definitely there is going to be a difference. And in a very simple way, the molecular interactions are not going to be the same, which means the efficacy will change. So yes, yeah, the short answer to it is yes, but I don't know the exact numbers.
Hello.
Yes.
Hello. May I ask you a question?
Please.
I am Gautam Biswas from APC College, Kolkata. What is the role of R0 value?
Yes, sir.
And another two is how we can arrive the herd immunity, and what do you mean by mortality rate?
I am not an expert in modeling, so I will refrain from saying much. I would urge you to go to the ICRAPMS website, because there is a lot of information. But very simply put, the R0 rate tells you the rate at which the entire disease can spread, and the mortality rate tells you how many people per thousand are getting affected by it. That's very simply put, but then for that you need a lot of numbers which are correct, which I think we're not getting. But regarding herd immunity, there is a lot of problem, because herd immunity would require that if you get the disease once, you develop an immunity, which itself people are not sure. If you read the literature over the last 1 week or so, it is not very clear that the immunity is going to be long term. It looks like it can be reinfected, which means the question of herd immunity is going to be difficult. But even if herd immunity were to work, the numbers for the older, diseases like influenza were, I think, about 65%. So you need a 65% of the 65 to 70% of the population to be infected and recovered for herd immunity to work. So I would say the best is to use masks. And I will not answer this too much, because I'm not a biology person, so it would be inappropriate for me to say anything more.
Okay, thank you.
Thank you, sir.
Excuse me, madam.
Hi.
Can I ask? As we all know now, we know that this virus, according to study, we know that the virus will strain with time. So my question is, how do we keep up with this virus? Like, how will we know when will it strain? What is the effect of this virus with the strain to our body, to mucus? Like, if there's more strain, will it affect more, or will it reduce the cause?
I didn't understand what you mean by strain.
Like, just recently I saw one study going on, like with time the virus will strain and the medication for it will differ. I don't understand, what do they
some kind of a mutation of it, like where it changes from one form to the other. Okay.
Yes, kind.
One thing is with any okay, let me answer this into just a slightly detailed answer. Right now, almost all scientists across the globe, except for very few, are stuck at home in lockdown, which means a lot of these studies which are coming in are either based on modeling or some kind of a previous experience with other diseases, right? So, and then, yeah, some measurements are being made and they're seeing that the mutation is happening and everything. Mutations happen all the time. So I think the epidemiologists and the virologists are well aware of it, how to handle it. So that's not a big issue, because the spikes will also be there and you are going to attack those, etc.
So if mutation happens, it can also happen that its effect will increase or decrease to human, isn't it?
Correct, but then you're hoping that the immunity is there to a certain extent by the time the mutation happens, and like I said, nobody really knows. That was what Peter White was trying to say, that you don't know enough. The more you know, the more you don't know. We are all in the initial stages where we are learning along with the virus propagation. Right. Even referring to the previous question about R0, the value for R0 has been changing over the last 3-4 months only because we are learning every day. The more the numbers come in, the more we learn. So it's, if you are, if you do modeling, you know that your model is as good as the data that you get. But the data itself, I mean, for various reasons, is very, very tricky. Like, we're not getting the correct data for many things.
So is other modeling that is going on accurate right now, or is it under study?
What modeling?
Modeling, like from the data, whatever we get.
Models that are there, and they're all, I would request you to go to the last website I mentioned. There is a specific, subgroup on modeling, and you will find all the models there.
Okay.
Yeah, that's a great place, and you can email me after this. If you feel like you still want to ask some questions, please feel free to email me. Let's let the conference go on. But I strongly urge you to go to the website and check with ICRAPMS. They have a huge section on modeling.
Okay, ma'am. Thank you so much.
You're welcome.
Hello, ma'am.
Hi, Dhanush. Nice to see you.
Hi. Yes, ma'am. Nice to see you, ma'am. A very nice presentation, ma'am. I have just one question, ma'am. Yeah. Like people are talking about the second wave, like still in India, we are not reached the peak. So when, when we will reach the peak, and what about the second wave? Is there any prediction about that?
Danuj, again, the scientific answer to this question is that we need numbers. When the scientists are given the correct numbers by the government and all the agencies that are associated, you can make a prediction. If the numbers are missing, what do you do? That's a simple answer. I think you understand what I mean. Right. The data is missing.
Okay. Okay, thank you, ma'am.
Thanks very much. Nice seeing you.
Madam, thank you very much. We had a very good interactive session. So I thank Professor Madhurima once again, and we'll go to the next presentation. We have.
Oh ma, দরজাটা লাগাচ্ছ কেন? দরজাটা খোলো। হ্যাঁ।
We have Dr. Hello.
Yes, sir. Yes, I can hear you.
Dr. Madhav Prasad Bhimire, a brief introduction about him. Assistant Professor, Central Department of Physics, Day1 University, Nepal, and IFW, Dresden, Germany. Luxem Institute for Solid State and Materials Research, IFW, Dresden, Germany. Have a Humbert postdoctoral fellow, National Institute for Material Science, Tsukuba, Japan, NIMS postdoctoral researcher, Nepal Academy of Science and Technology, Malipur, Nepal, senior scientific officer. His awards and achievements are Vidya Bhushan Medal from President of Nepal, 2018. Awarded Humboldt postdoctoral fellowship, Alexander von Humboldt Foundation, Germany, November 2015. Nominated for 66th Lindau Nobel Laureate Meeting 2016. WAS Grant, CWAS Award 2011 in Physics, Third World Academy of Sciences, Italy. He has been awarded the NAST-INSA Bilateral Exchange Program, INSA India 2011. He has significant publications in Nature Materials, Physical Review, Nano Letters, etc. His presentation today is creating wild nodes by magnetization rotation in chrome metal EOCSN2S2. So I request Dr. Bhimire to make his presentation. The time allotted is 25 minutes, and there will be 5 minutes interaction session.
Yes, thank you very much for the very nice introduction, Dr. Samir Bal, principal and the main organizer of this international conference, e-conference. It is really a matter of pleasure for me to present some of my work in this platform, especially where I have my supervisor in front of me and my teacher, who is the chief guest, Professor Madhurima, my supervisor, Professor Dr. R.K. Thapa, even my students here and scientists from across the world. So it is really, really, really a matter of pleasure for me. I'm very, very thankful to my junior bhai, who is Amit Shankar, who invited me to give a presentation. And I'm representing Tribhuvan University, which is another pleasure as well. Okay, so yes, without taking much time, I just thanking all the organizers, Christian College, and then St. Joseph's College, principal of St. Joseph, Father Donatus Kujur, who is really very kind last time also. He invited us last year. And then present all those speakers, presenters, and participants. So today I'm going to present here my recent work that has been published in Nature Materials. Sorry that the title I have a little bit changed. I will try to, within this 30 minutes, I will try to bring 15 minutes for the most important part that I try to address. Sorry, there is some sort of background noise. Yes, if there is, can you please help from the hosting side? So I will be sharing first the iron tin, which was published in Nature Materials, and then another very important paper of mine, which is cobalt-3 tin 2, and then so can you see my screen?
Yes, sir, we can see your screen, sir.
Okay. Yes, thank you very much. So this is the first part of my talk, which I will briefly talk, though my students and some of the audience have already known about this material, but most of the audience which I have seen are still unaware about this particular material, which is very, very interesting. And this is a big achievement, at least for me as an author. That's why I would like to share with you. So please bear with me. And yes, the first part of my talk is on Dirac fermions and flat bands in the ideal Kagome metal, iron tin. And then, yes, going further. Okay, so this work, after its publishment, it got well recognized in universities also. And that's why this is the image where it was published in our website and in several medias. So this is the outline of my talk. I will be discussing the basic concepts of the Dirac fermions and the flat bands, and the type of semi-metals, because most of the thing that we understand is either metal or semiconductor or an insulator, but we used to usually neglect the semi-metallic phase, which is really very interesting. And today I will try to discuss about those two important parts. And then I will discuss about the crystal structure of the material, particularly focusing on this iron tin. And then the results, iron tin and then cobalt-3 tin 2 sulfur 2. I think I'm audible. So here on the first section, I will be discussing about the Dirac nature of the iron tin. And on the second section, which is the topic title that I have given, here this is the results where I will be discussing about the creation and annihilation of wild points in a Kagome system. Okay, so let us start with the basic concept so that everyone is clear, because many of us are students. I can see that. That's why if I give this general picture, which is well known to teachers and to many of the students. So let us see here. This is the figure where I have a sub number given as A, B, C, and D. So if you look here, this is the schematic band picture, wherein the dotted line represents the Fermi level. And above the Fermi level, there are some sort of empty-like features. So this indicates the conduction region. So above the Fermi level is the conduction region. And then below the Fermi level, this is the occupied region, which is shown with a dark feature, as you can see. So what we try to distinguish from here or try to understand is that the bands, these are considered as the band, or let us say the band structure, those who are doing the DFT calculations. So the bands are crossing from the, going from the valence region, which is below the Fermi level, to the conduction region, and they are crossing the Fermi level without any sort of gap. So this indicates that the material is a metal. Similarly, if we go to sub number B, what we understand clearly now is that there is a gap in between the this band, which is called the empty or the conduction region, and this the occupied region, which is the valence region. There is a gap which is something of an order of 4 electron volt, means the gap size is really very large. So indicating that this is an insulator. And then when we are discussing about the semiconductor do also have a gap, but the size of the gap is really very small. Now, depending on the material, whether it is an element, for instance, silicon or germanium, the gap size will be something in between 1.1 eV to 0.6 eV, so at room temperature. Now, as you can see, this is the gap size, but if the, it is in the compound form, the size may be still very small or large as well. Okay, now this is the most interesting part, which I called it as D for my discussion section. So please have a look here. What you see is, so this is the momentum space. In the momentum space, when you are going, when the energy is rising, so you see that there is a valence region, there is a conduction region, and they are touching each other somewhere at the Fermi level in the dotted sign. So this indicates that if you increase the temperature, it may happen that it may go to metallic state, or it may happen that it goes to an insulating phase. I mean, the variation of the temperature or other different factor like pressure can change the feature. So in that sense, this becomes very interesting. So that is the main motto here. And now, when we are discussing about this semi-metal, let us see what is on the right hand side. This is important, that's why I'm taking a little time here, just not more than a minute, I will assume. So this is a trivial insulator. What you see here is a gap in between the valence region and the conduction region. There is a gap you can see here. And then if you see here, what you see is a semi-metallic where they are each other. But the interesting thing is there is a new kind of material which has recently been found. And for that, the Nobel Prize has been given as well. So that is a topological insulator. So if you see there, so semi-metal is lying in between insulator and trivial topological insulator, wherein due to the inversion of the band, the gap appears again. So you see what is the difference between this trivial insulator, which has a smooth gap, and then the topological insulator, which has something like different nature of the gap. So this is because of the band inversion, which I will not discuss much, but I just try to tell you that semi-metal lies somewhere in between these two. That's why the nature of this semi-metal is very, very important. Now moving on to our main topic. So today we will be discussing mainly on the issue of Dirac fermions. So what is Dirac fermion? So as we know, states means the band structures plays a very, very important role, and the electronic band states where spin and orbit of the electron are coupled to each other. The nature of that phenomena is the Dirac fermions. And these Dirac fermions are particularly protected by the topology, and then the geometry of the structure varies accordingly. And this is particularly the Dirac fermions are modeled by the Dirac equation. So in this work, what the main significance, which you already have known, I suppose, is about the 3D analog of graphene, which was recent in 2004. The graphene was found out to be a 3D analog of, Dirac semi-metal. And because of that nature, it has a very high, unusual conducting state, which I will show in the next slide. Apart from these Dirac fermions, another important point is the flat band, which people usually neglect. But this flat band, in terms of our band structure, if I show you here, for instance, what you see is the schematic band picture here. So in this schematic band picture, there is FB noted. So this notation is called as the flat band. And here Dirac cone, so DC is the Dirac cone, which is generated from the Dirac fermions, which we discuss here. So flat band are really flat, means they are dispersionless, such that throughout the Brillouin zone, you will find that they are almost flat, indicating that if you try to dope somehow, then it may give rise to very, very interesting properties that I'll be discussing later. Okay, so here I have some sort of points, but thinking about the time, let me go a little bit faster. So let us come back now to the 3D semi-metals. There are two types of semi-metals that we discuss usually. One type of semi-metal, which we call is a Dirac semi-metal, and this Dirac semi-metal is nothing but it is a doubly degenerated bands. Means that the two bands are overlapping with each other, which you can see from the feature. Am I too fast?
Sir, I think you're okay.
Okay, thank you. So, and please remind me 5 minutes before my ending of the time. Yeah.
Sure, sir.
So here what we see is that the red and green indicates that there are two sort of bands which are doubly degenerated and they are overlapping with each other. And they also form like a Dirac cone-like feature, as you can see here. And because of these properties only, they are very, very useful, which I will show you on the next slide as an example of this graphene. So let us see here. So graphene is a very, very good example of Dirac feature. Here you have a graphene like a graphene sheet. And this graphene sheet was found out by these two guys, Gaim and Novoselov. And because of this work, they have been awarded with a Nobel Prize in 2010. Okay, why? Because this Dirac type or Dirac semi-metal system has a zero effective mass. And then it has a very high mobility, excuse me. And then robust, it is very robust and survive even at room temperature and has high electrical current, thermal conductivity and stiffness. So because of these features, this becomes very, very novel. Now going little, yes, so now going to the wild semi-metal. So what is wild semi-metal? So it is basically a non-degenerated bands. So what you see from the double degenerated bands, they are splitted. So when they are splitted, you can separate them out with these red features as well as green features. So there are many, many examples. One of the experimental example is tantalum arsenide, which is a type 1 semi-metal. Okay, so these systems are also very, very applicable in spintronic devices. So here are some of the important applications that, there are important properties they give rise to, such as the chiral anomaly effect, strong intrinsic anomalous and spin Hall effect, large magnetoresistance, and so on. And because of these natures, they are also applicable in quantum computing. Why? Because they are less prone to interacting with the environment due to their chirality conservation. Chirality conservation, when I say, means they have too short of chirality as they are non-degenerated, you can see here, with positive chirality and the negative chirality, which forms a Fermi arc, as you see here on the right side. So there is some sort of excuse. Yeah, this is one of the example of the 3D Dirac semi-metal, zirconium telluride T5. Can you please? I'm sorry. Okay, so this is a three-dimensional Dirac semi-metal in observed experimentally by angle resolved photoemission spectroscopy. So what you will see here is in experiment, because RPS only measure the region which is below the Fermi level. So below the Fermi level, what you notice is a Dirac cone-like feature exactly here with some sort of cone. So this is done by DFT calculation further and have confirmed that, okay, the nature of is the band inversion nature, as you can see here. So this there are two short of crossing. One crossing is this one, as you can see here. The another crossing is this one. So this implies that there are two short of bands, Dirac bands, which are crossing with each other in this particular material. So from this information, what we get is that a single system can have a number of Dirac points. Now coming on to our project of this iron tin. So these are my collaborators from MIT, from Harvard University, from IFW Dresden in Germany. So he is the person with whom I'm mainly working during my Humboldt Fellowship program. These are the two postdocs from the same institute, and he is our director who is handling this project. Okay, so what I would like to start with is that the work that we have presented got published in Nature Materials, after which, when it got published in Nature Materials, so it came up as a news and views as topology and correlation on the Kagome lattice. And fortunately, it turns out that Nirmal J. Ghimire, who is the CDP alumni, who is also my collaborator right now, they are writing the work of us as a news and views. So it was really very nice to experience this also. So basically in this, what we try to report is that we explore the new type of Kagome lattice, and then we found that this single element has two types of nature. One type of nature is the Dirac fermions that I already discussed what its application is, and then the flat bands which it has unlike the other materials. So let us try to discuss in more detail about it. So here, this is the Kagome lattice. When I say Kagome lattice, so Kagome lattice forms a structure of this form. So basically in Nepal, we have a Tribhuvan University logo, which is of this type, like a basket, basket with an eye or with holes. So Kagome comes actually from the word of Japanese, which is eye, a basket with an eye. So this is a basket with an eye. And because of this, this shows the nature, which is triangular in form. There are two laths cross and has four neighboring points. Let us say this is one lath, right? And this point is covered or surrounded by 1, 2, 3, 4. So this sort of system will definitely give rise to the Kagome-like structure. So there are many types of Kagome system, but our system that we are going to discuss, let us focus directly onto that. So this is our system, iron tin. So in this system, what we have is one layer of our system is Kagome, which is surrounded by the iron, and at the center we have tin. And on the second layer is completely of the tin alone, and the alternating layer is again iron 3, then tin. So this is the structure that we have for our particular system. So let us try to understand.
5 minutes more, sir.
Oh, only 5 minutes. Okay, thank you. So yes, in that case, I think I will just try to wrap up with this Kagome, the first section only. So Kagome features, in this case, what we have is that they have a different type of properties depending on whether they are magnetic or non-magnetic. When they are non-magnetic, then they give rise to Dirac semi-metal-like structure, which is as shown in the graphene. And if they are non-magnetic, means ferromagnetic or ferromagnetic, they can have different properties. So let us say this is ferromagnetic. When it is ferromagnetic, it has all the spins up, and then when you apply spin orbit coupling, what happens is there is a gap generated in between. So in my structure, what we have is we have one layer which is iron 3 tin, and the another layer which is purely stannine SB. I already discussed about that. So this is the crystal structure. Let me know to go much onto this. So this is the band structure that we have computed from our DFT calculation. And then throughout the Brillouin zone, we consider the integrated density of states and could find that at K point, there is a crossing which is observed also in experiments. So let me focus onto that. So in this system, what we found is, this is the FE3SN2 is the another system which our MIT group has explored 1 year before, and basing on that, we also look onto this one. So what is there? We observe different Dirac cone in this system. So this is the angle resolve photo emission spectra that is taken, and then we could observe that in this system there are 3 types of Dirac bands. Okay, so this is my experimental section. So here what we consider from experiment is that we consider 2 short of cutting. So when we are saying 2 short of cutting means we consider the termination, because when I have iron and tin, then you know that one of the layer is iron 3 tin and the another layer is tin alone. So if that is the case, I can have 2 short of termination. And if on the 2 end I have only kagome, then I call this as kagome termination. And if only tin is there, I call it as tin termination. So here what we consider is, we consider tin termination, you can see it here, SN termination, and on another is the kagome termination. So basing on the different termination, we see very interesting feature, and that interesting feature is that if you consider tin termination, there are 2 Dirac cone existing on this particular material, somewhere below the Fermi level EF at around 0.2 to 0.43 electron volt. And similarly, so this is the snapshot from the KY direction. So you can observe where the location was exactly. So you can see that. And similarly, when we consider the kagome termination, what we see is there is 1 Dirac cone. So based on that, we consider the surface calculation from our DFT, and we could see that, okay, when it is SN termination, we observe what is found in experiment. Where here you can see red is there and yellow is there. So there are 2 short of Dirac cone, Dirac cone which are appearing in this feature. And in this case, you can see that there is 1 Dirac cone in kagome termination. So these are the position which I will not discuss, and then because of the time, what I will say is that, okay, so from this, the first main breakthrough is the synthesis of this particular material as a single crystal and then to explore the surface state. And the second breakthrough was the unique properties that it gives rise to, which is a flat band and then Dirac cone-like feature. Well, I forgot to mention about the flat band which was lying here. So let me show you the where we find the flat band. So this is the Fermi level. Just below that, you can explore. You can see that under LV polarization only, we can observe the flatness of the band. And basing on that, we consider the DFT calculation as well. Okay, so yes, just to give a very brief overview of wild semi-metal. So wild semi-metal, we already noticed that they are the non-degenerated bands which are splitted from the Dirac semi-metal. So they will have 2 short of chirality. One is with positive and one with a negative, and because of that, they form this Dirac Fermi arc at the surface. And depending on whether they are having perpendicularly exactly at the Fermi surface, they are called as type 1. If they are tilted somehow with respect to the Fermi level, they are type 2. So this is the main findings that we have, as I said. So this was published in the as a rapid communication and physical review research. And my collaborators, as I said, these are the peoples from MIT and Harvard, as well as IFW. So let me go directly onto the main section. So we have actually checked for first whether it is a real Dirac Weil semi-metal or not. So what we found is that when we consider DFT calculation, we observe that it is a Weil semi-metal, of course, and it is just above the Fermi level, somewhere around 0.4 EV, with 0.4 to 0.7 EV. So they are. And we consider a magnetic rotation. Yes, 2 minutes, please. So we consider magnetic rotation. When we are saying magnetic rotation, what we say is that we align the direction of the spins first along one of the hard axis, which we call it as a C axis, and then we apply a magnetism, rotate that spins in this way along different direction, and we end up on the another plane, that is in plane, which is called 100 direction. So here what you are seeing, just have a look here. So theta is equal to 0 correspond to the C axis, and pi by 2 corresponds to the 100 magnetization. So we rotate the magnetization in this way. So as we rotate the magnetization, the very interesting thing that you find it in this picture is that the Weil points lie somewhere around 0.7 milli-electron volt above the Fermi level, and then up to 45-degree rotation, it remains on the same energy scale. But as you go further, what you find is they are moving closer and closer to the Fermi level. So 0 corresponds to the Fermi level. Our interest was basically to move the Weil points close to the Fermi level or at the Fermi level so that transport experiment would be possible. That's why, so we look from the KXKY plane, and you can see here the Brillouin zone. So this is how it is rotating. The rotation of the motion of the Weil points at, along different direction. So dotted are the annihilation, and the real line are the creation and the motion. Okay, with that, we consider anomalous hole conductivity as well as Nernst conductivity. Because of the time limitation, I'm sorry that I have to end up in this way. Here, what we find is Weil points are created and annihilated with the rotation of the magnetization. And we find 1, 2, 3, 4, and 5 positions at different angles where they are crossing exactly at the Fermi level. Means that we can find out the transport experiment easily. Thank you all. So this is my group.
Thank you. Am I audible?
Yes, please.
Thank you, Dr. Ghimire, for your excellent presentation of your work you have done in Germany, Japan, and Nepal. And because of the time constraint, we will go to the interaction straight away. So, if there are any questions asked,
I think ICRAT Z has some question here. ICRAT.
Yes, please.
Ikra Zahid. I think she has one question.
Yes, please.
Assalamu alaikum, sir.
Walaikum assalam.
So my question was, what is the main difference between semi-metal and a semiconductor?
Well, yes, as I said, so semi-metals means it shows the conducting nature at the Fermi level at 0K, okay? And the semiconductor has a very minute band gap. So depending on whether it is an element or a compound, the size of the gap may vary. Let us say, if it is silicon, it has a 1.1 EV of gap, right? And if it is germanium, it has 0.6 or something like that of gap, which is quite large. But if it is an compound, let us say Ba2Ni or some double perovskite compound, it can have even a very smaller size of the gap. So they are either semiconductor, you call it, or nowadays they are also called plate. But semi-metal is that, yes, they have very, very, very finite, very small density of state at the Fermi level. Is that clear?
Yes, sir, got it. Thank you.
Any other question?
Hello.
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 May I ask one question, sir?
Yes, yes, go ahead.
Yes.
Madam, sir, I want to ask you one thing, sir. In semiconductor also the two bands are the two bands are they are closely there is no band gap in a semi-metal, as well as there is also not any band gap existed in a metal. What is the difference between the metal and the semi-metal?
Okay, a good question anyway. So in case of metal, when we say metal, you know, so definitely they are crossing from the Fermi level, but when you are saying about metal or pure metal, the density of a state at the Fermi level is very, very high. Let us say, for instance, iron, okay? So iron, the density of state at the Fermi level is very, very high. But for the semi-metal, the density of state is very low. Just one or two bands are crossing at the Fermi level. Very, very small. So that is how you can distinguish semi-metal to metal.
Hello. Hello.
Yes,
Hello.
Gautam. Yes,
Very much, sir.
Since it is a crystal structure, so how you can determine this heavy atom crystal structure, and what is the space group of this?
Can you repeat your question again, please? Sorry, I could not hear properly. You mentioned about crystal structure, right? Gautam Biswas. Yes, please.
Hello.
Yes, I
Can
can
you
hear.
repeat the question?
Hello.
Sir?
Hello.
Yes. Yeah, I can hear you. But I think
Can
he was saying about the iron tin. If you are asking about the case group, it is 191, which has the carbonyl-like feature. Okay.
Hello.
Yes, please.
Where is the method in DFT calculation? Is GGA or PVA?
Yes.
What is the method in DFT calculation? Other question, what is the term Hubbard? What is the value for you?
Thank you, Hugo. And actually, it is a GGA, Generalized Gradient Approximation calculations. We don't need the plus U calculations because it already addressed the electronic properties experimentally. So what we were looking is whether it is showing the similar feature as observed in experiment or not. So with GGA, we are able to cope up or extract the information that we require for.
Excuse me, sir.
Yes, please.
We will take the last question from Nakul Chetri.
Please.
Mr. Nakul.
Hello, sir. Am I audible?
Yes, Nakul Chetri.
So this is Nakul Chetri from Raiganj University. So in the energy gap, in energy distance, in energy graph, we have seen that the valence band and the conduction band, they overlap one another. Therefore, how can we calculate the band gap, sir? Can we use band structure calculation to calculate the band gap, or we need to use some other method? The first one. And the second question is, so what is the potential significance of semi-metal compounds when they are doped with suitable material for physical significance in future aspects, sir?
Okay, thank you. Yes, so when the band are crossing, conduction band and valence band are crossing, then they already signify that they are they are metallic in nature. But if the density is high at the Fermi level, they are pure metal. If they are low, they are very low. They are semi-metal.
Sorry.
And the second question that you ask is, what is the significance of a semi-metal? Well, all semi-metals are not at all significant. No. Only those semi-metals are significant which has two sort of properties. One is Dirac-like semi-metal, wherein there are doubly degenerated bands cross near or at the Fermi level. If they cross near or at the Fermi level, like a graphene. And because of that, they have very zero effective mass and very high conductivity. Magnetoresistance also. That's why they are very, very applicable. Now, when coming to the case of wild semi-metal, which is also a semi-metal, so they are just non-degenerated because of the different features like band inversion, and then time reversal symmetry broken, etc. So because of that, what happens, they are splitted up, and when they are splitted up, they are able to exist, or the wild points are able to exist at the position without affecting by any of this environment. And because of that, it is expected to be a very good candidate for the future computing device. There are many applications, but one is that example. And of course, it is also applicable for magnetoresistance and so on.
Excuse me, sir.
Thank you.
Excuse me, sir. Sir, one more last question from Hugo Medina.
Okay, please.
Johannes, I have a question.
Yes, please.
Hello.
Yes.
Hello.
You can ask your question, Medina.
Thank you.
I can hear you.
I have a question too.
One question, please. In the semiconductor, you have one band gap in the order 1.1 electron volts. What is the criteria when you use term Hubbard and you DFT calculation for the semiconductor metals? Is based in experimental results or in theoretical results?
Well, see, as I said earlier, so depending on whether the system is in element or compound, the band gap size differs. If it is the case of silicon, you know that the band gap size is 1.1, which is very large, right? But if it is for a compound, the size differs, means it can be very, very small as well. So when I have
for this material is very, very small. For the other metal, band gap is the major order.
Maybe I don't get your question again. Can you please repeat that?
Yes.
So this, are you asking about my system that I have done, or you are asking a general question?
General question.
Okay, please, can you repeat? Sorry.
In your material, your band gap is the order 1.1 electron volts. Okay.
Yes.
Yes. In the other materials, band gap have other values. 2 electron volt, 3 electron volt, depend of materials. Okay.
Yes.
What is your criteria? Where is your basket when you use a DFT calculation for calculate band gap and structure bands?
Okay. So if I understand correctly, I hope I understand your question. So yes, when we are doing DFT calculation, the measurement, whatever we have done is at 0K. This is known to all of us, right? And when, let us say that I have a compound with an experimental information at room temperature that the gap size is 1.1, but my DFT calculation only predicts about the 0K. So in that case, what I have to do is I have to explore the crystal information from the 300K fit into my DFT calculation, and I do the measurement. And based on that, the gap size, you will definitely notice that size will be quite close to what experiment is found. So that is how I do. Or else, if it is a correlated system, I have to apply the plus U, and I increase the or decrease the size of the gap.
Okay,
Did I
thank
answer
you.
your question?
Thank you.
Yes, thank you.
Thank you, Dr. Gimire. Due to time constraint, we could not take all the questions. Maybe those participants who have any questions to ask can contact.
Yes, if they have any questions, sorry, if they have any questions, they can write me on my email. And if they are interested, of course, they can collaborate as well. Thank you.
Thank you. Thank you. Thank you. Dr. Amit?
So yes, sir. We can move to the next part. The speaker.
No, your program schedule in one phase there is oral presentation. The other is PK Das. Let's start with PK Das.
Yes, sir.
Okay.
Hello. How are you?
We'll have.
अच्छा मैं यहाँ busy तो ल ल
Das. He's a postdoctoral researcher in Deep Earth Center for Earth Evolution and Dynamics, Oslo, Norway. He has done his MSc and PhD from Jadavpur University. He has been awarded Newton Baba Fellow DST and British Council in 2016-17. As I told you, he is holding the position of a postdoctoral researcher in the Center for Earth Evolution and Dynamics, University of Oslo, Norway, and Newton Baba Fellow, Department of Earth Science, University College London, UK. This presentation or topic for discussion or this presentation is material behavior under extreme conditions, a DFT approach. So, may I request Dr. Pratik Kumar Das to make this presentation. Thank you.
Thank you, Professor Ball. Can you see me?
Yes, yes.
Okay, let me just share my screen.
I can hear you very clearly.
Okay. Can you see my screen?
Yes, yes. Clear.
Zoom will able to record the contents of your screen until it's good. Hello, am I audible?
Yes, yes, you are audible.
Yes, you are.
Okay, so good afternoon, everyone. So Professor Ball has already introduced me. So I will just jump into my topic today. So today the topic of my presentation is minerals behavior under extreme condition, a density functional theory approach. So we know the basic consideration of DFT is the ground state energy is the functional of the ground state electron density. So in DFT, we play with actually the energy and its derivatives. So using this DFT, I am going to focus on some geomaterials which are equally demanding in industry, as well as their study helps us to understand the behavior of our Earth. I am going to concentrate mainly on the three major type of phases, these sulfide, silicates, and oxides. Nowadays we are living in the era of material science. So everyday life, every electronic device we use comes of materials. Even in the nuclear industries, we need some refractory materials in the furnace and materials for energy storage, for hydrogen storage, or to store highly heated nuclear waste. So from material science research, we get olivine sands, olivine bricks, zircon rods, and they are widely used in furnaces nowadays. So the preliminary aim of my research is to characterize some geologically important mineral phases so that we can use them in our everyday life as well as in industry. So first, I want to talk about zinc sulfide phases. So here you can see in the left-hand side, it is the zinc blende structure, and in the right-hand side is the rock salt or NaCl structure. So zinc blende has a well-known phase transition from B3 to B1 phase at around 18 GPa. So, but we know natural ZNS always comes with some impurities of like iron, nickel, cobalt, etc. This study aims to investigate the effect of these impurities on the physical and electronic properties of impure ZNS. Thus, I choose Fe as an impurity with variable concentration. So I use the supercell approach for these simulations. So I use substitutional defect mechanism while incorporating iron in the zinc sulfide structure. Here you can see the B1 and B3 phase, which are the first one is 12.5% Fe doped and second one is 25% iron doped. And these iron positions are chosen in a nicely way where this system has the minimum energy. So using these structures, I begins my simulation. The first thing is to draw the equation of state of these structures. Here you can see these are the equation of state for pure 12.5% and 25% structure. And this is purely the energy volume curve. And from there, we can calculate the enthalpy. And here the enthalpy versus pressures are plotted for the two phases. And you can, and their crossover denotes the transition pressure from B3 to B1 phase. In the pure phase, you can see I got the transition pressure around 17 GPa, whereas the increasing Fe content decreases the transition pressure up to around 13 GPa with up to 13 GPa. So you can see this is the phase. If we draw the phase diagram with iron concentration, we see a inverse relation with the increasing Fe content. So but this is a preliminary work what I have started with. Our main aim is to investigate their mechanical and electronic properties. To start investigate their mechanical properties, I started with the elastic constants. So you can see as the pressure increases, the elastic constant increases almost linearly in for C11, which is the principal directional constant, and C12. But the mysterious thing is the C44. You can see for the B3 phase, for pure as well as the Fe doped phase, it decreases. So we can say that this B3 to B1 phase transition is purely shear driven, and the same transition for the iron doped case will happen earlier because of the more softer C44. You can concentrate on this green line. But this C44 softening is also associated with our the phonon modes. So this results leads us to investigate the lattice dynamical behavior of the system. Using lattice dynamics, I have plotted the phonon dispersion of B3 phase at ambient condition as well at high pressure, which is little higher than the transition pressure. The lower frequency, I started this calculation with a primitive cell of zinc sulfide. That means which contains 2 atoms. So for the phonon modes, we should get 6 phonon modes. Among them, 3 are acoustic and 3 are optical. The lower frequency modes are the acoustic modes. At the ambient condition, we found stable acoustic modes here. But when we go to higher pressure with the same crystal structure, we found negative acoustic modes. So the physical significance of this negative acoustic mode is just the structure is unstable. We cannot found this structure at this pressure. So as we already know from the phase transition curves that after 17 GPa, that B3 phase transform into B1. So this result supports our calculation. Secondly, we are also interested in the electronic properties, and because ZNS is already used as a wide bandgap semiconductor. So here we found the band gap is 2.8 eV, which is little bit lower than the experiments. That's because you know, the GG always underestimates the band gap because it overestimates the volume, and this later we extend our study with the same study on the iron dot cases. Here you can see finite but unequal number of states in the even at the Fermi level. So this includes that this structure turns into a conductor one, but with some magnetic moment. So to conclude this study, we can say the transition such impurity has an inverse relation with the phase transition, and this impurity can lead semiconductor ZNS to be a conductor. Now I will try to concentrate on the silicate phases. So I have studied many silicate phases, but and all these phases because they are highly incompressible and they have very high heat resistive capability. So I will discuss only two of them, olivine and pyroxene, because they have so many similarities from the structural point of view, but different physical properties, which are my point of interest. So in the left hand side, you can see olivine, which is a nesosilicate with isolated SiO4 tetrahedra. Whether pyroxene is a chain silicate, that means it is characterized by SiO4 tetrahedral chain along C-axis. This blue tetrahedra correspond to the SiO4. Both olivine and pyroxene structures have two distinct cationic polyhedra. They are namely this M1 and M2. In olivine, they comes in a different layer, like M1 layer, then M2, then again M1. But in pyroxene, you can see they appears just side by side. In both cases, generally the bigger cation occupies the M1 side. So my aim was to study the effects of cation ordering in these sites, in these octahedral sites, and the effects of this cation ordering on the mechanical and electronic properties of these mineral phases. So I again start with the elastic constants. I plotted a lot of calculation elastic constants here because this is an orthorhombic system. I have to calculate the 9 elastic constants for each type of each phases, because so here in the left hand side the 9 elastic constants of olivine are plotted, whereas in the right hand side you can see the pyroxene. So the you can observe the main thing here, the C55 elastic constants. This is basically denotes the shear modulus of the system. You can see the cation ordering has a large increase at ambient condition, and this gap increases as the pressure increases. Whereas in case of pyroxene, all the shear elastic constants have the similar effects at ambient. They don't have any significant effect, but as the pressure increases, the effect is become more prominent. Using these elastic constants, I calculated the directional shear modulus. So now you can ask what is the point of using calculating this directional shear. You can understand this while I go to the next part of this slide. So first I want to say, as C55 is directly related to the directional shear modulus along the C plane on the BC plane on the C axis, so it directly we get the direct consequence at the directional modulus of G13. It is the same effect as C55. Whether in pyroxene, it also the same, we can see the same effect as C44, C55 and C66. Now, the other aspect of this work is to relate the seismic discontinuity of Earth. As we know, the olivine is responsible for the Hell's discontinuity, that is 410 to 660 kilometer discontinuity of Earth. We investigated the wave velocities in these phases because these two phases are abundantly available in the upper mantle of the Earth. So type 1 to type 2 ordering causes an inverse effect in olivine and pyroxene. In olivine, In case of olivine, you can see the shear wave velocity decreases at ambient condition, but with pressure, it becomes nearly same. And it also agrees with our experimental value by Liu et al. This star mark is the values for Liu et al. Whether in case of pyroxene, you can see there is a jump in the shear wave velocity even at ambient pressure, and which stays almost equal at high pressure. So this study this jump in pyroxene corresponds to the discontinuity of the Hell's discontinuity. So nextly, for the electronic properties, I investigated the density of states for the type 1 cathode phases of pyroxene because olivine is already well studied. So I calculated the density of states for at ambient and high pressure. So in the left figure, you can see some magnetic moment where the magnetic moment vanishes at high pressure because you can see the finite and equal number of states in for both up and down spins. So to conclude, we can say the cation ordering has a significant role in the shear softening, and they give rise to some metallicity and ductility to the olivine phase at very high pressure. Nextly, I will come to the oxide phase. So this where I started with my DFT calculations long back 2015 or 13 probably. So I studied the sequential phase transition in the SNO2 phases because it has transition from rutile to CaCl2 to alpha PbO2 to CF2 phases. So in the upper panel, you can see there is the energy volume curve, and I measured the transition pressure from this curve because from the common tangent method. Even I applied the what is called enthalpy crossover, where the enthalpy difference of enthalpy is plotted with respect to the rutile phase. So this black line is the rutile, and these crossover points denote the transition pressure. So our transition is reported as rutile to CaCl2 to alpha PbO2 to CF2. Later, here again the elastic constants are plotted against pressure within their stability range. So from this sequential phase transition, we can say that these transitions are purely shear driven, as the pressure derivative of the shear modulus is nearly unity or negative. The elastic constants allows us to look into the directional anisotropy of this tetragonal and orthorhombic phases. As the rutile type is tetragonal, so it has for the crystal structure, it has two axes are same, that is A and B, and C is different. So I have calculated the two directional anisotropy, that is A1 and A2, whereas in CaCl2 and alpha PbO2 they are orthorhombic. So I have to calculate the three different anisotropy directional anisotropies. The significant part of this plot is in the alpha PbO2 case, you can see a strikingly different nature, and almost all this anisotropy shows a reversal at around 18 GPa, which suggests a more typical crystal mechanical behavior of this phase. Thus, we examine the Young modulus surface at ambient and high pressure. I found that the Young modulus surface is totally distorted, but we can assume we can think if we plot them the directional projections on different planes. So here is the projections. You can see for rutile and CaCl2 type, the ratio of Young modulus along the diagonal and as well as in the axial direction on AB and BC plane, they increases with pressure, which suggests the elastic stiffness become more anisotropic at higher pressure. Whereas the alpha PbO2 phase shows contrasting behavior of the directional Young modulus. Sorry?
5 minutes more.
Oh, sorry. And on the AB plane, the modulus increases along the diagonal, and when the pressure increases to 30 GPa, you can see the stiffness ratio goes almost doubled. So from these findings, we can conclude the elastic structure, the crystal structure of the alpha BO2 phase becomes more planar and compact at high pressure, which you can see from this, which is missing in other two phases. Later, I calculated the density of states again at ambient and high pressure. Here you can see the multi-peak structure of alpha PbO2 type at the 40 GPa, which is missing in CaCl2 type. So this multi-peak structure denotes the planar structure. And another thing to notice, you can see the band gap, which increases with pressure. So the band gap evolution of all these phases with pressure are plotted here, and this increasing band gap makes as they have luminescence properties, this increase in band gap make them industrially very demanding. So these are the conclusion of this work. I will skip this. Next, this is the last work what I have done at SEED. I studied 3 major silica phases which are available in the different part in different depth of our art. So I will start with the equation of state. I already told that GGA always overestimates the volume. So this black line, thick black line, is our equation of state, which is almost 12% higher than the experimental data. So we made a correction to this GGA result. That is nothing but a shift with the negative shift of pressure, and you can see the it lies on the experimental value, this black dash line. So with this, after this correction, we started our calculation with the transition pressure, because their transition pressure is well studied but not well verified. So here I used 2 types of functionals, GGA and hybrid one, and found that hybrid always predicts little bit higher volume, higher transition pressure than GGA. So this is at the static level. So after this, later I used the QHA to explore the high temperature properties of these phases. The difference of the Gibbs free energy is plotted against temperature with increasing pressure control. The phase transition is denoted when Gibbs free energy difference becomes negative. So this is the basic thermodynamics. So thus the intersection point will give us the transition temperature. The outcome of this 2 figure in the left panel, you can see the transition temperature increases with pressure, because they will see the pressure derivative. You can see the pressure, the temperature increases with pressure, resulting in a positive Clapeyron slope. Whereas in the right panel, you can see the temperature decreases with pressure, which means it will result in negative Clapeyron slope. So here is our final phase diagram. These 2 thick black lines are my results. So it is already with the it already agrees well with the experiments. Now we concentrate on this negative slope. There was a previous study who did this same calculations with LDA, and they found a 10 GPa lower, but almost the same slope. So, but they never explained why the slope is negative. So the point is, we explained why this slope is negative. As we are going to a high pressure transition, so our volume change is always negative, and the Clapeyron slope is denoted by change in entropy to the change in volume. So if we get a positive Clapeyron slope, then our system will have a negative entropy change followed by a negative volume change that results in the positive entropy, positive Clapeyron slope. Whereas in this case, this transition should be characterized by a positive entropy change. So we have to look on the entropy of the system. So it can be done from the vibrational density of states. So we plotted them at the transition pressure, and if we integrate these states, that is it will give us the entropy. So if we just concentrate on the lower frequency region, you can see that beta stishovite has higher population than cyphertite. So as the cyphertite is the high pressure phase, so if we subtract the entropy from cyphertite to beta stishovite, we will find a negative change of entropy, so which supports our result. Secondly, if we go for the cyphertite to pyrite transition, the pyrite has the higher one. That means this transition is supported. This transition is supported.
Sir?
Yes.
Sir,
Just 2 minutes
is
more.
up. Okay, sure.
and then this transition is characterized by positive entropy change because pyrite has more population. So our as the volume change is negative, we will find the negative Clapeyron slope. So to conclude this work, I can say that the cyphertite has a higher stability range and long stability range, and the HSE works better than GGA, and it has some implications from the geological point of view because it helps us to get the seismic discontinuities, even the seismic velocities, because our art is made of almost 15 to 20% of basaltic material, and silica is the most prominent thing in the basalt. So it can help us to understand the art also, and that's all. Thank you.
Thank you, Dr. Das, for your presentation on the in-depth studies on material behavior under extreme conditions. Maybe because of the time constraints, you can't put everything in your presentation.
You're welcome.
We'll have one or two questions, interactive questions, one or two, then we'll go to the next presentation. If there are any questions, queries, or any inquiries.
We have one question from Nihar.
Yes, please.
Nihar? Please go ahead with your question.
Hello. Am I audible?
Yes.
Am I audible? Hi, I'm Prashant from ICTS TIFR.
Hi.
When you talked about the Clapeyron slope, you said that the entropy change is negative, right?
Yes.
Isn't this against the second law of thermodynamics, which says that change in entropy is always greater than or equal to 0?
No. It's because Clapeyron slope is defined as del S del V, as we are going to a high pressure phase transition, and so our del V, that means the change in volume is always negative, right? So if we get a positive Clapeyron slope, so our del S always comes to be negative from the mathematical point of view.
No, yeah, mathematically I understand. I understand that you're getting this even in calculation, but isn't this contradictory to the second law? That's the question.
No, because if you go for a phase transition, it is going to a different phase. So if you use the same temperature or something, then you will go to the higher entropy. But when you are comparing a different phase, it doesn't say in the thermodynamics like that, right?
Okay, any other questions?
We have one more question from Dr. Suvankar.
Okay, so you have studied SNO2, you have calculated SNO2.
Yes.
So there is another thin oxide which is SNO. So can we use SNO, or what is the why SNO2 not SNO? Any comment on that?
Okay, I haven't studied the SNO, but it have like different phases, and I don't know it has some sequential transition or not. I just studied the sequential transition and the reason behind this transition. So I showed them as these transitions are shear driven, and I found how much shear will how much is dependent on the shear, and how will it depend on the transition pressure and their electronic properties. But I haven't studied the SNO. So if you found there is transition or something, you can study that.
Thank you.
Just one follow-up, please. This time. Can I go ahead?
Yes, I can hear you.
Yeah. So regarding that negative entropy change, the systems that you're looking at, are they equilibrium system or are they non-equilibrium system? Because in non-equilibrium, we know that there is possibility for the entropy change to be negative. There's room for that violation of second law. But in equilibrium, there's no room, right?
Yes, you are
I don't.
right. But when we are comparing two different phases, we can't compare, no? Because if you are comparing like same phase at different pressure and different temperature, your entropy will always go higher and higher. But if you are comparing two phases at same pressure, then you have to compare the entropy to know which one has the stable one. You have to look for the energies, and when you look for the temperature dependent energy, your entropy comes into the picture.
I don't know. That's not very intuitive to me, but maybe that's correct. Thank you.
Anyways, if you have any more question, you can just write to me.
Yeah, sure.
I am happy to answer.
Yeah, thank you.
And that's for everyone. If you have any more question, you can just write to me. I am very happy to answer.
Okay, thank you, Dr. Das, for your presentation. We'll move on to last presentation.
You are welcome, Professor Paul.
So we have the next presentation will be made by Dr. Divya Prakash Rai. He is the assistant professor in the Department of Physics, Kochunga University College, Aizawl, Mizoram. He is a postdoctoral fellow in the group of Professor Tan Heng Ki in Computational Science Research Center, Beijing, China. He has in his name a patent, Noble Booster Control System for fully automated driveless vehicles. Publication date is 18th of October 2019. He has more than 50 publications with him. And today we'll be speaking on thermoelectric properties of fused alloys. So time allotted is 25 minutes and 5 minutes discussion. So may I welcome Dr. Divya Prakash Rai to make his presentation.
Okay, thank you, Principal Sir. And is it clear?
Yes, I can hear you.
Okay.
The light behind is reflecting on your face. That's it.
Maybe I have to shift some. Just a minute. Can I share the screen?
Sir, you have not shared your screen.
Okay.
Yes, sir.
Is it okay?
Yeah, you are audible.
Can you see the screen?
Yes, sir. Yes, sir.
Yes, we can see it.
So, without wasting time, because I have a short time, only 25 minutes, so I'll start. So, first of all, I would like to thank our principal, Dr. Bal, and coordinator, Dr. Amit Shankar, and Dr. Himanshu Joshi. Thank you very much, guys, for this good time. So today I'm going to talk about the electronic and thermoelectric properties of Hissler compounds. So I'm working on this compound since around 8-9 years. So I have even my PhD topic also in Hissler compounds. So I'm an assistant professor in the Department of Physical Sciences Research Center, Kochunga University College, which is the constituent of Mizoram University. This is my location. Currently, actually, I am from the localites of Kaohsiung, but now currently I'm working in this institute, which is located at northeastern part of India, and the name of the city is Aizawl. Aizawl is more likely to any of the Himalayan cities or the Himalayan towns. So, and currently our university is 51 rank in NIRF university ranking. So this is the basic description about my institute, where I am working. On the outline, so first I will talk about the introductions, then I will talk about the previous research and promising results that have been already found out and the techniques and all. Then the selection of compounds, which are the compounds that basically fit for the, like the said topic or the said applications. And I will talk about the description of the calculations in brief, and I will talk about my results and discussion and conclusion. So the present crisis, in introductions, I will talk about the present crisis, because present crisis is all deal about the energy crisis. Everyone knows that, and the pollutions of the environment. So now we have to deal with such kind of energy which is eco-friendly, as well as which will give the the desired performance that we are looking for. And now the material science is one of the field in which we are looking into for search of such kind of energy, okay, which gives higher energy output by conversion, like solar energy, which has been absorbed by the materials and it will be converted into electrical energy or the usable form of the energy. Similarly, the wind energy, water energy, or and such like that. So I'm talking about thermoelectric. Thermoelectric is a kind of energy which is the materials which will absorb the heat, and those heat will be converted into electrical energy or usable form of energy. So that is the main concept here that I'm dealing with. And what is thermoelectricity? First of all, we should know about the thermoelectricity. Thermoelectric materials, or not all the materials are thermoelectric. That means you apply the heat and it will give the electrical, response. That is not possible in all the materials, but there are certain materials which will, behave like that. Types of materials which absorb heat and convert into electricity, or vice versa. Okay, so those kind of materials are called thermoelectric materials. So application of thermoelectric materials, I have already said that it will be used for producing a small amount of energy, or that will be used for our home appliances and all. So how does these materials work? So these materials work. Here you can find out different types of thermoelectric materials. One is N-type, another one is P-type. They have made the clusters of N-type and P-type. It's just like a cell. So batteries of cells, it looks like. So here what will happen is one end of this system is heated up. That means it will absorb the heat, and the other one is the heat sink. This side is the heat sink, and this, the N-type, the red one is the N-type, and this green one is the P-type. So you can have the two terminals. So so the two terminals will be there. So when you apply the heat, at one end, then what will happen? The potential difference will be created. The potential difference will be created. Then the electrons will flow from one end to the another end. So for N-type, when the electrons will flow from one end to the another one, then its tip will be negative terminal. Similarly for the P-type, at the end, the accumulation of the hole will be takes place, and that will be your positive terminal, and the connection of two will be a circuit, kind of circuit. Okay, so thermoelectric effects. We have in our in the undergraduate classes, we have studied about the different types of effect, thermoelectric effect. So the first one is the Seebeck effect, another one is the Peltier effect, and the third one is the Thomson effect. The production of, in the first one, that is the Seebeck effect, the first one is the production of electromotive force. Okay, when two junctions are maintained at two different temperatures. So if the two junctions are having the two different temperatures, suppose the top is heated and the lower one is cooled, then there will be a potential difference between the two ends. So this is a Seebeck effect, and another one is the Peltier effect. Peltier effect is just the reverse of the converse of the Seebeck effect. This effect will give you some and heating and cooling effect when you apply the one end of the materials will be cooled and one end of the materials will be heated up when you apply the electric field. So this is just the converse of the Seebeck effect. Another one is the Thomson effect. Thomson effect is just like absorption of or the evolution of the heat when you apply the electric field. It's just like like any conductor, when you apply the field, the conductor will be heated up. So it's just like that. So the applications are here. Thermoelectric materials. Why thermoelectric materials? We are looking into it is because that there are numerous sources that heat has been wasted from the car engine, even from our kitchen, kitchen cooking, and from kitchen stoves also amount of heat has been released, and from the factories is the main source of heat, which releases a high amount of heat. If we accumulate that heat into usable form, then that will be of great help for solving the energy crisis. So here are some of the examples of some foreseen applications of the thermoelectric materials, like portable refrigerator. In portable refrigerator, we can use this Peltier effect. So Peltier effect can be used to get this thing refrigerating effect. And cooling blanket also, it's possible. Then wearable jackets, that air conditioned one, which we can wear during the summertime and all. Then the logical circuits also, it's possible. I have no idea about this logical circuit actually. And these are some examples. I've already talked about the beverage coolers, and when you heat this one, this materials which contains a lot of thermoelectric cells, and when you heat it up, it will generate the electricity. And the laser diode cooler, etc., has been foreseen for its applications. So which materials are good for thermoelectric applications? The materials whose efficiency is greater than 1 are good for, or equivalent to 1 are considered as good thermoelectric materials. Even though the materials which is having efficiency equivalent to 1 can give around 20 to 30% of applicable energy. So how will you measure the efficiency? The efficiency of these thermoelectric materials can be measured by a formula that we in our in our papers or in our type of studies, we generally call those who are of this background, they knows it, and we call it figure of merit. The name of the efficiency is called figure of merit, and this is denoted by ZT, which is given by S square sigma T divided by K. Here S is the Seebeck coefficient of the material, sigma is the electrical conductivity, T is the absolute temperature, and K, that is called the total thermal conductivity. Okay, so K actually composed of two parts. One is the thermal conductivity because of the electrons, and another one is the thermal conductivity because of the lattice vibration. So requisites for getting high value of efficiency. So which are the parameters that we have to look into to get the higher efficiency? So the higher efficiency can be achieved when you have a higher Seebeck effect, because it is in the numerator and plus it is square. So we need a high materials having the high Seebeck effect. And second one is high electrical conductivity. And the third one is the low lattice thermal conductivity or low total thermal conductivity, because the thermal conductivity is totally, dominated by the lattice part. So, these things, three things we have to look into our the systems for getting the efficiency, the better efficiency. So, if you see this one, where will you find the high Seebeck effect, and where will you find the high electrical conductivity, and where will you find the low lattice thermal conductivity? So metals are good electrical conductors. So electrical conductivity is very high in metals, as well as if the electrical conductivity is high, if we know that metals, like the transport, the charge transport or the electrical transport is governed by these Weismann and Franz law. So at the same time, the thermal conductivity will also increase. The electron part of the thermal conductivity will also increase, but the metal will have definitely low Seebeck coefficient. Okay, so and the semiconductor, the second one is semiconductor. Semiconductor is having a very high Seebeck coefficients, but it has low electrical conductivity. Again, there is a controversy like which one to be choose, either the metal or semiconductor. Metal is having a high electrical conductivity, but Seebeck coefficient is low. And semiconductor having the high Seebeck coefficient, but electrical conductivity is low. Electrical conductivity is low. Another one is the non-crystalline type glass. Glass is found to be the such kind of materials which is having the lowest electrical conductivity, but the glass is non-crystalline. Okay, and again the Seebeck coefficient of glass is very low, and electrical conductivity is also very low because most of the glass are insulators. So that is the problem we are dealing with. Either metal or semiconductor, forget about the glass, because glass is completely insulator, and moreover dealing with the non-crystalline structure is very complex. So theoretically maybe a tough, we haven't dealt with the non-crystalline type of system. So so this is the reason why metal or semiconductor, which one is to choose. If we choose the metal, its electrical conductivity will be high. At the same time, the thermal conductivity will also be rise up. So they will, like suppress each other. And another thing is like semiconductor. In semiconductor, what will happen is the Seebeck coefficient will be very high. So these are the materials. I mean the properties, how we choose the materials. Here you can see this one. The K value is very high in this kind of this one, because the electron and phonon coupling is very less out here. Okay, very less and insignificant out here. So that's why it is having a high lattice thermal conductivity. Here in this kind of, if you see the phonon frequency graph, you can see there is the coupling between the electron and phonon coupling is prominent. So in this case, the electron and phonon coupling will give you the low value of K. So this is one of the criteria where we should look for low K value. Another one is the high dense bands. So if the energy bands are very dense near the Fermi energy, that will give you the high value of Seebeck coefficient. So here in this kind of bands are very efficient for getting the high value of Seebeck coefficients. So these are the, the properties that we have to look into our materials for getting the higher value of our efficiency of the materials. So here in this paper, I have read this paper, and this paper is very interesting. This paper talks about the doping. How will you dope these systems to increase the Seebeck coefficients of a semiconductor, and how will you, dope, what kind of materials will be doped to get the suppress its lattice thermal conductivity. So they have discussed here in this paper, this is Nature Communications in 2015, they have talked about the two types of bands. When you are studying about the band structures, probably you will be getting with the two types of bands, one type of band or two types, depends upon the materials. Okay, so so the first one is the light band, then heavy bands. Light band and heavy bands. You have to find out which one is the light band and which is the heavy band, and which one is more better for the getting the higher Seebeck coefficient and doping. Okay, when you dope, what will happen is it will suppress your lattice thermal conductivity. So the light band is not good for doping, because here the saturation point is very low. The saturation point is very low. Because of that, you cannot dope more amount of dopants. So that is the reason. So the light band materials are not good thermoelectric materials, because the density of the states is not that dense near the Fermi level. And another thing is, it will have the light band will have the higher lower effective mass. If the effective mass is low, then the motions of the charge will be high, or you can say the charge mobility will be high. So we can say in that sense, if the charge mobility is high, then electrical conductivity will also be high. So that also a very interesting thing. But at the same time, if you come for the this flat band or the heavy bands, what will happen is you can have more number of dopants. You can dope more number of elements, because of it has not reached the saturated point. Okay, so it has not reached the saturated point. So flat bands will generally give you the low value effective mass. Low effective mass will be electrical conductivity will be low. But at the same time, it is giving the two advantages. The first advantage is it allows the doping. Once you dope, what will happen is it will create more number of states at near the Fermi level. Once you have the more number of dense the bands near the Fermi level, then your Seebeck coefficients will increase. Okay, Seebeck coefficient will be high. Then another advantage is when you dope these structures, what will happen is it will scatter more number of phonons. If it scatters more number of phonons, then it will resist the flow of the heat waves. It will resist the flow of the heat wave. In a way, we can say that the that is part of the thermal conductivity has been checked. In some extent, we can see. But what kind of materials, what kind of elements should be doped? So here we have talked about the two bands, light band and the flat bands. Okay, but in the flat bands, they have shown two structures. Okay, one structures with the pink color ball, 3 balls are there. Those are the dopants. And in the third one, they have shown 3 blue color balls. If you see this figure, this pink color ball is smaller than the blue color ball. Okay, what does that mean? That means the atomic mass of this blue is bigger than the atomic mass of the pink color. So while doping also, if you dope the heavy elements, then the scattering rate will be high. If the scattering rate will be high, then it will check the flow of the heat that will suppress your lattice part of the thermal conductivity. Some of the significant progress in the thermoelectric materials. There are so many thermoelectric materials, but why we are dealing only with the Hissler compound? The reason is that the Hissler compounds, its efficiency is now almost over 1 or equivalent to 1, and the working range of Hissler compound is very high. So that means the Hissler compounds can work for a high range of temperature. Even if you increase the high amount of temperatures, the phase transition will not take place that easily as in other kind of compounds. So that draw our interest for this kind of work. So approach. What kind of approach we are using for dealing with these materials? How we are dealing? So the way how we are carry out our research work is that we are contacting few of the experimental people. We are a complete theoretical group. We are not doing any kind of experiment. Hello?
Yes, sir. 5 minutes more, sir.
Okay. I will finish it. So here we contacted the different types of different groups, experimental groups. Once they will publish the paper, or once they will generate the systems, we will be in contact with them. We will take their system or with their materials. Then what we do is we design it as per our wish. Design means we just module the system, I mean the materials. How we do is like either if you want to do the doping kind of work, we will dope the system. If you want to make the layer, we make the layer. If you want to make the, I mean the nano crystal, we just put the vacuum or we just cleave it to a surface. Then then we do the calculation. The calculation first we start with the optimization. Optimization means we change its shape or size. We change its size and we try the different SCF calculations to, I mean the self-consistent type of cell calculations to get its minimum energy. Once the minimum energy we achieved corresponding to the different lattice parameters, then we proceed our further electronic calculations with that system, okay, by using density functional theory. So this is the type of structure that I mean the system or type of materials that we are dealing with. The general formula for the Hessler compound is given in the black box here. Sorry, not the formula, that the position, and the most of the Hessler compounds are phase center cubic. Okay, phase center cubic. So their lattice parameter is same throughout. That means cube has all the sides equal. It ranges from 5 to 6 angstrom, and the positions of the different atoms are given out here, A, B, C, D. So there are 3 types of Hessler compounds. No, actually 4 types of Hessler compounds. One is binary, ternary, and quaternary. So only 3. Sorry, binary, ternary, and quaternary. 3 types of Hessler compounds are there. So this is the position of the ternary compounds. So here A stands for A000, B stands at the position half, and C is 1/4, and D is 3/4, 3/4, 3/4. Okay. So if you take A, B, C, A is any transition metal, and B is also a transition metal. C is the any p block elements. Either you can check aluminum, carbon, nitrogen, anything. Okay. So that will give you the these things. So nitrogen is not possible. I think that's a gas. So, but along that line, you can find out other p block elements. So the D will be generally, sorry, this will be like this. So this D will be the final one. So now, if you go for ABC, that means A and B is same, and C and D is different. Okay, suppose Fe2COL, for example, Fe2COL, there are A and B is same, C is CO, and D is the Al. Okay, so that is your full Hessler alloy.
Excuse me, sir.
In full Hessler, yes.
Your time is over, sir.
Just can you give me 2 minutes? Let me wind up this. Okay. So let me wind up these things. So the selection of the Hessler compound is very, very important. We are selecting the semiconductor because metal, they said here. The second one, if you come to the second one, if you the total valence electrons is 18. So 18 minus 18 is 0. So this compound is semiconductor. You can see the band gap is exactly lying in the Fermi level. So this is the semiconductor. So this kind of material is good for the thermoelectric calculations. So how these bands are formed here, this one is because this band is formed because here A and B is the 3D elements in the DD hybridization will take place. Once the DD hybridizations will take place, then what will happen is the bonding and anti-bonding states will be formed. Bonding state means where the states are completely filled up. Once the state is completely filled up, that will have the lower energy, and those states which are empty, that will go above the Fermi level. So the like the measure of the difference of these two energy difference is the energy band gap in the semiconductor. So we use Y2K. Why we are using Y2K is because there are many softwares based on the density functional theory, but we are using Y2K. The advantage of the Y2K is because it will take all the potential starting from the nucleus up to its the valence electrons. That is one advantage. One is that it has plenty of tools and gap. For other systems, if you have to go for the band gap calculations, you have to go for hybrid type of calculations, or you have to go for GW type, that green function approach, which is very, very expensive. But in Wine2K, the good thing is that it has plenty of other options which will improve the band gap, like GGA, GGA, MPJ, DFT have, all are within the local approach. So they are, the convergence time is same as GGA. So that's why we are dealing with the MPJ. So this is our results. This result has already been published in Journal of Applied Physics in 2018, 17 or 18, I don't know much. So this is the semiconductor system, and this is the semiconductor system. And this is the half Hessler compound. This is SFPTPV type, and so we also got some kind of couplings there, electron proton couplings. So we thought this might be a good thermoelectric materials. So and for calculation of the this one lattice thermal conductivity, we have used the Slack's equation, which is much easy and can be easily yes.
Sorry, sir, we are running out of time, sir.
Okay, this is the result, and these are the latest publications that we, the relevant publications that we deal with. And I would like to thank my supervisor, R.K. Thapa. Because of him only, I'm into this research, and with his help and support that I could complete my research, and now I'm established assistant professor in like Central University, and my senior MP Gimire also, which is also very helpful, and which is very knowledgeable, to help me a lot. And thanks to Persian College and my alma mater, St. Joseph College, the convener, the two young conveners, Dr. Amit and Joshi. Thank you, guys. Thank you.
Thank you, Winda.
I organize the best one.
Hello.
Hello, sir.
Hello. When the world is facing with the energy crisis all over and the pollution, very interesting presentation by Dr. Rai. Thank you very much. And now we have their doubts if they have.
Hello.
Hello.
Hello. Abhijit Nath. I think Abhijit Nath has one question.
Okay.
Abhijit.
Hello.
Hello, Abhijit. Can you hear us?
I think Abhijit is not online.
And next is
mute the microphone. Hello.
Hello.
Yeah, hello. Yeah, we can hear.
Hello.
Go ahead. If there is a problem, we can go to the next.
I think there is no more question.
No, what was the question? I didn't. Hello, Dr. Amit.
Hello. The participants, they will ask you a question in chat link because we can't connect to anyone. We have one question from Ravinder, I think.
Okay,
Hello?
yeah. You can read the question, or Ravindra will directly ask me.
Yeah, hello. Yeah, you can ask your question here.
I think there is no question, so we can proceed with the next session.
Okay. Thank you, Dr. Rai. So we have 4 presentations in the technical session today. And
Nakul, it seems that Nakul has some questions. Amit, please. Hello, sir.
Okay.
Nakul has some questions. He has said he has some questions in the query box.
Okay.
Hello.
Hello.
Go ahead, ask your question.
Hello. So am I audible, sir?
Yeah, it's clear.
Sir, you talked about the property of substance to be a thermoelectric material.
Yes.
And initially you started with the pure material, sir.
Yeah, I have studied in the pure materials.
So then you talked about giving it dope and then layering and giving it a nanostructure. So can you explain in short the difference between these three method of improving the quality of the
You
thermoelectric
mean doping? In doping, what will happen is like, if you see my this thing, in the doping, what will happen is because of the heavy elements, okay, the vibrations will be less. The vibration will be less. If it because the size of the dopant is very high, the vibration is high because the heat energy will transfer because of the vibration, right?
Yes, sir.
So that will be checked by if you dope with the heavy elements. So if the transfer of the heat is less, then obviously its thermal conductivity will also be less. So layering of this structure means you have to make the layer, okay? If you add some, if you make the layer of these structures, what will happen is the interface will act as a barrier. In terms of, you are layering structures, what will happen is the barrier will be, the interface will be act like a barrier to the heat transfer. So that is the reason.
So what about giving nanostructure to the materials?
Nanostructure, if you give, what will happen is it will drastically change the electronic properties, right? So if you change, if you could manipulate your nanostructures so that you will get the dense energy bands near the Fermi level, so that will increase your Seebeck coefficient.
So therefore, these three modes have different significance, it seems.
Yes. The layering and the layering of the structures that means the two different materials should be clubbed, okay, but you have to make sure that there should not be any lattice mismatch, okay. And doping will be, if heavy element will be there, then generally it looks like a resistance to the heat flow.
Thank you, sir.
Okay.
Thank you very much, Rai. Now I hand over to convener for next announcement.
Thank you,
Dr.
Samirval, and Principal, Costing College, and for coordinating this session. And now we have come to the end of this, our inaugural session, followed by the first technical session. Now we are moving to the next presentation, that is the oral presentation by the participants, and one more presentation from Dr. Amitabh Bhattacharya from Department of Physics, Sikkim University. So before going into the technical session, that is for the next technical session, that is oral presentations, I would like to request Professor R.K. Thapa, retired Professor R.K. Thapa, Department of Physics, Major University, to kindly coordinate our technical session. Thank you, sir. And before that, one more announcement. Please, one more announcement to all the participants. Dear participants, please kindly mute your microphone. Dear participants, please kindly mute your microphone. And one announcement. Now, after this first technical session, we're moving to the oral presentation, like I said. Now, in the oral presentations, we have one presentation from Dr. Amitabh Bhattacharya, Department of Physics, Sikkim University. And just followed by the lecture, we will be moving to the oral presentation for the participants, where we have the parallel session. I have shared the link in the WhatsApp group. And for the next session, this session will continue here, and another parallel session link I have already given in the WhatsApp link. So choice of participants is up to you. Choice of participants is up to you. In this session, the continuation of this session, we have the presenter, Ms. Ispita Rai, and Mr. K. Manjunatha, and Mr. Vishnu Karki. So they will be talking about the structure water chains in external electric fields. The second one, the bismuth, doped cobalt, chromates, nanoparticles, a detailed study of structural, microstructural, electrical, and magnetic properties. And the third one is the noble topological wireless semi-metal phase in the lead material F2SN. So the area of their research are mathematical modeling, magnetic materials, and spintronics. Those who are interested to listen their lectures or the presentation, you can stay here. And those who want to go for the next, the other session, that is paper presentation by Ms. Neetu Sharma, Ms. Suraksha Thapa, and Mr. Dibankar Kalita, they will be presenting their work based on the nano and the biomedical applications and the particle and nuclear physics. If you want interested in this session, then you can shift to the another session where the link has been provided in the WhatsApp. And if you want more details about the participants, last night only I have said one link in the WhatsApp where the detailed program details you can find out. Okay, so we have now the oral presentation where Dr. Amitabh Bhattacharya will present his work, and after that we will split into the parallel session, and we will have the choice where to move. Okay, fine. Thank you. Please kindly, Professor R.K. Thapa, please, I request you to kindly coordinate the session.
Okay. Hello. Thank you very much, Dr. Amit. Before we start the session, am I audible? Hello.
Yes, sir. Yes, sir.
Yes, sir. Okay. So before I start the oral presentation by Dr. Amitabh Bhattacharya, I take this opportunity to thank Dr. Samir Bal, a principal from Kershin College, as well as Dr. Kujur, Dr. Father Kujur from St. Joseph College, and my students, Dr. Amit Shankar and Dr. Himanshu, who are coordinators respectively, for giving me this opportunity to stay these sessions. Now, without wasting any time, so we have now oral presentation by Dr. Amitabh Bhattacharya from Sikkim University, which will be followed by technical session as already informed by our convener, Dr. Amit Shankar. So may I now call upon Dr. Amitabh Bhattacharya, who will be giving it oral presentations on science behind the unsung Indian musical drum. So may I request him to start with the presentations, and I believe the time is 8 plus 2 minutes for these oral presentations also. If I'm wrong, please, Dr. Amit, correct me. So may I call upon Dr. Amitabh Bhattacharya.
Good afternoon, everyone. Am I audible?
Yes.
Good afternoon. Am I audible?
Yes, audible, please.
Okay, good. So let me begin by thanking Dr. Thapa for chairing the session, Dr. Amit and Dr. the coordinator and the co-coordinator, Dr. Samir Bal and Father Donatus Kujur, for organizing this conference. And then, without getting into anything else, let me straight away start my work. Please allow me to share my screen. Can I share my screen now?
Yes, sir. Yes, sir. Your screen is showing.
So I would like to speak about the science behind the unsung Indian musical drums. So let us start. So music has been important to mankind right from times of antiquity, as we can see in this, the sculpture and the engraving where people are playing musical instruments. Musical instruments have been classified in many ways, and the basic thing is what kind of vibrations are producing the sounds. The first classification was by Bharat Muni in his Natya Shastram, which was written in the 4th or 3rd century BC. So he said that if an instrument produces sound by vibrating strings, it is a Tatavadya. If it is vibrating air column, it is Susiravadya. If it is a wood or metal object which vibrates itself, that is Ghanavadya. And if it is a drum or an instrument with a skin head, where the skin head vibrates, that is the Apanabhavadya, which literally means covered instrument. So the same very classification was produced in an extensive way in 1914 by Eric Bornmaster and Kurt Sachs. He said chordophones use vibrating strings, aerophones use vibrating air column, idiophones vibrate themselves, and membranophones are devices with vibrating membranes or drums. But as we know now, most musical instruments work on electricity, and these are the electrophones, which was added. Now let's go to our old man whom we know a lot, Pythagoras, who was born around 570 BC. He explained that if we have two stretched strings whose lengths are in the ratio of two small numbers and strike them at the same time, we produce a pleasure sound. So since the frequency of a string is inversely proportional to its length, the frequencies are also in a ratio of small numbers. So these are what are called harmonic overtones. And any string instrument, be it the guitar or be it the veena, produces harmonic overtones of rapidly reducing loudness. So there is a base frequency, the lowest, and its integer multiples, like double, triple, 4 times, etc. The frequencies produced follow a ratio of 1, 2, 3, 4, and this makes it pleasant to the ear. This is what it looks like. This is what it looks like. The fundamental, the whole string vibrates. In the harmonics, there are notes in between which do not vibrate. What happens to a drum, an ordinary drum? It is just a stretched membrane. It produces the sound, true, but there are no harmonics, no overtones. The different frequencies do not have any links, and this is called an instrument of indefinite pitch. Now we have a few special drums in India. These were called musical drums by Sir C.V. Raman. As you can see here at the right hand bottom corner, there is a black circle on the drum surface. That is called siyahi or tuning paste, It is a heavy material which has been put there in a certain way. And these instruments, examples are mridangam, pakvaj, khol, madal, pung, nal, dhime, mandar, the Sri Lankan hoki, and most popularly seen the tabla. They have a definite pitch. Like here are the pictures: the mridangam, pakvaj, tabla, madal, and pung. The oldest member, the senior-most member of this family is the mridangam. We sometimes see Ganesha, sometimes see Nandi playing it. As per the myth, it was designed by Brahma after this playing of Tripurasu, and he himself trained Ganesha to play. Of this category, the best known is the tabla. It has two drums, one very small, one very big. Small was made of wood. The large one is either clay or a metal. Both membranes have this black circle called syahi. They are played vertically and they produce harmonics, clear pitch, and tonal possibilities. Let us look at the physics behind it. The wave equation of a stretched membrane is given by this equation, the second order differential equation. And since it is circular, we can write the equation in r and theta coordinates, assuming that the membrane has a uniform mass per unit area and uniform tension per unit length. So we take the u function into r, theta, and phi. U, r, theta, and t, phi is not needed. T gives cos omega t plus phi, no problem. Theta is cos m theta plus psi. So for some values of theta, there are no vibrations. These are the total diameters. It is the r function which is interesting, which gives us the Bessel functions. So this is the complete equation, the Bessel function in cos m theta, cos omega m and t. The boundary condition is no r equal to a, that is the end of the drum. So u r theta t is equal to 0 at r equal to a, which means that j is 0 at these values, which gives us these values of k. Now the Bessel function zeros we do not have any integral ratios. Hence, a drum like this cannot have harmonics. Now, how do we get the harmonics? Of course, we have to make it. So the tabla, when you make it, 4 different kinds of people are needed. First of all, you need a carpenter to make the right hand tabla. You need a potter or a metal worker to do the left hand. This is just the body. Then you have to put the leather worker comes in, he puts in the leather, tightens it, and fixes it. And then comes the most specialized thing to apply the syahi, the black patch on the top. It is this black patch which will do the magic. Here I have put a closer picture of the right hand of the, not the tabla, this is the madal. And you can see the concentric circles of the syahi. Within that, can you see cracks in the circle, apart from the concentric rings? Can you see cracks? So first you put a layer of a paste, a plant paste, and then layers after layers are put of either iron filings or iron oxide mixed with paste. That is either floor paste or dice paste. And after putting every layer, it is rubbed with a stone. The stone rubbing is important. If we don't have the stone, we will get a hard material which will not vibrate. So you have to rub with a stone to get cracks so that the material becomes flexible and the membrane can vibrate. Now the gravest mode of vibration is the diameter, where the whole screen vibrates up and down as one unit. In the first harmonic, there is a diametric mode, so the two sides vibrate separately. Second harmonic, it's divided into 3 parts. Third harmonic into 4 parts, etc. And then we have a properly assembled tabla. Now, this is what I explained, the fundamental first harmonic, second, third, fourth. So, if we now try to solve the equation for a loaded drum, the equation becomes, and it can be solved only numerically, and this is the solution. Now, some amount of contemporary work has been done. The pitches, the frequencies have been studied. It has been found that the frequencies are not harmonic. The fundamental is 1.07 is to 2 is to 3 is to 4, not 1 is to 2 is to 3 is to 4. What happened is C.V. Raman did not notice it. And some people, the reference is given below. The reference is given below. It's have tried to model the sound production, and they have been able to get up to 2 harmonics. They also tried to load a Western drum. They chose the kettle drum, which is shown, and loaded it by fixing rubber sheets and produced 4 harmonics. They again found that the fundamental is not 1 but 1.07. Should we try to modify it, or is it not necessary? No music lover or no musician has ever been disturbed. Now another thing is, what should be the shape of this CIE? Should it be a flat screen, flat disc? No, it will not produce harmonics. Should it be a linearly decreasing thickness like a cone? It will produce no harmonics, as has been shown below. If the thickness reduces logarithmically, like I have shown here, you will get a harmonics. And this is the reason why one CIE, one side CIE, takes a full day of hard work. And this person does not know logarithmic decrease. He does it entirely by hearing, by the ear. In conclusion, the tabla, the mridangam, the pakhavaj, the khol, the pung, the madal, also the mandar, the dholki, these are drums which produce sounds with a fundamental and overtones. And these are indispensable in Indian classical music. You cannot have a classical concert without one of these instruments playing. And it is because of this rhythm and harmonic tones that we have one performer with a few accompanists performing in classical concerts. Very unfortunately, like many things in India, the origin of these instruments is lost in antiquity. But still, a scientific understanding which was started by C.V. Raman and is being continued is required to improve the design and, more importantly, to preserve this unique heritage. This is something which is not seen outside of the Indian subcontinent. To finish with, let me thank the organizers of the conference, all these people for helping me to do the work, and the mobile phones, the internet, and the long-lasting laptop battery to let me do the job. Finally, thank you very much for your attention.
Okay, Dr. Amitabh, thank you very much. You're almost in time. Now, as we are running out of time, so quick questions for 2 minutes only, please.
Professor Thapa, this is Madhurima here.
Yeah, nice to hear you. I have seen you this morning.
So I just have a quick comment for Dr. Amitabh.
Yeah.
I teach a course called Physics of Arts, which includes physics of music, dance, and painting at my place. And I think what you have just presented is very contemporary, very much required. And the nuance of, how a kettle drum does not have harmonics, whereas our Indian instruments do have, because of the tie, is a very interesting point. And I should thank you for bringing this to the public. Thank you very much on behalf of, many artists.
Thank you, Dr. Madhurima. Thank you very much. Any other question, please? So if no questions are there, I think we can proceed to the technical sessions now. Now, as already... Hello.
Hello, sir. Just a small announcement.
Okay, please.
To the participants.
Okay.
Now we are heading towards the parallel session, and the link for the another room, that I say, it's already given in the WhatsApp. So as per your choice and the research area, you can shift to the, either you can stay in this session or you can shift to the another session that is going on to the participants. Thank you, sir.
Okay. So we start with the technical sessions now of oral presentations. As already mentioned by Dr. Amit Shankar, we have 3 participants in this session. Now I call upon the first one is Smita Rai from Sikkim University, and the title of her presentation is Structure water change in external electric field? Smita Roy, please.
Good afternoon, everyone. My presentation is on structured water change in external electric field. These are my contents. So basically, water clusters, they are just hydrogen bonded assembly of water molecules. And this kind of water clusters, they usually form closed structures with these dipole moments. But when these water clusters, they are like confined in nanocavities or in nanochannels, they do not form closed structures. They rather open up to form elongated structures. Like, for example, in one of the studies, they have found that fused cyclic water hexamers are found in the channels of 3D supramolecular framework. Also, water hexamer ribbons are found in metal complexes, and ribbons of cyclic water pentamer are found in metallo-organic framework. So this kind of elongated structures, they have a specific like a geometric pattern, and this kind of structures, they are not stable in isolation. However, whenever confined in nanocavities, these structures exist. So, and when this confining framework is removed, the system collapses and it gets back to its closed form. So now we are interested in studying this kind of structural water clusters in the presence of electric field within the density functional theory. And here we try to study how the structure, its energetics and electronic properties evolve with the electric field. So for our study, this, we have taken the structures like first is a water tetramer chain, wherein the basic unit is a tetramer water ring with 4 water molecules. And here we have chains of water tetramer chains. So the shortest chain, it comprises of 4 units of tetramer rings, and the largest or the longest chain comprises of 8 units of water tetramer rings. Next, we have water pentamer chain, where the basic unit is a 5-membered pentamer ring having 5 water molecules. The smallest water chain has 3 units of pentamer rings, and the largest chain has 8 units of pentamer rings. Likewise, we have water hexamer chain with the basic unit of a hexamer ring comprising of 6 units of water molecule. And this, again, here, the shortest chain has 3 units of hexamer ring, and the largest has 8 units of pentamer rings. So here we have 3 units, 4, 5, 6, 7, 8, and 8 units of water rings. Next, now considering these structures, we have tried to optimize the system within the Gaussian system suite of programs in the presence of electric field. The level of theory chosen is B3LYP with the standard basis set of 6311 plus GDP. And this level of theory is used both for geometry optimization as well as for frequency calculation. So considering these structures, we have applied electric field, and we have increased the field gradually in steps of 0.001 AU, and the field range considered is 0.005 to 0.22 AU. So moving on to results. So we have first is hydrogen bond length. So we have tried to understand how our hydrogen bond length it evolves with the increasing field. Like and when we talk about hydrogen bonded system, we talk about cooperativity effect. So here, what happens is that in such system, with the increase in the number of clusters or with the increase in the number of water molecules, the hydrogen bond it strengthens. So like with the increase in the number of hydrogen bond, in the number of water molecules, there is a shortening of the hydrogen bond. And if we see here for tetramer chain, we see for 3 units, the average hydrogen bond length is 1.881. And as we go from 3 to 8 units, it decreases to 1.802. Likewise, if we check for pentamer, tetramer, and hexamer, we see that the pentamer chain has less average hydrogen bond length in comparison to tetramer and hexamer. So this decrease in hydrogen bond length, we attribute it to the cooperativity effect in hydrogen bonded systems. Next, we have tried to study the evolution of dipole moment with respect to the field. So here, the first plot is for tetramer chain, the second is for pentamer, and the last is for hexamer. So if you consider this particular plot, we see that with increase in the field, there is an increase in the dipole moment, and the dipole moment values for each like unit, they are relatively, I mean, they are high. So which means, and this is basically because of the arrangement of the water molecules, which are arranged in almost same direction. Next, we have plotted the average dipole moment for water molecule in the chain. And here we see that dipole moment for the pentamer chain is the least, followed by tetramer, and the highest is for hexamer. So here the pentamer chain has the least average dipole moment per molecule. Next, when we come to binding energy, here this energy, like how the energy, our energy stability, we have tried to understand it using this binding energy formula, wherein here we have calculated binding energy using this formula, wherein here EC is the energy of the cluster, NC is the number of water clusters, and En is the energy of water monomer. So here, if you see, we have plotted binding energy with respect to field, and also we can, from here we can study binding energy with respect to the cluster size. So if you check for 3 units, we see that with the increase in the field, there is an increase in the binding energy. The system becomes, so like the system grows in energy as with the increase in the field. Also, if you see here, the binding energy for 8 units is greater than that for 3 units. So we can see that as the system grows, it gains energy continuously. But also a closer look at it reveals that these 3 units, which has just 3 units, which is a shorter pentamer chain, it can sustain its structure for a very wide range of field. Whereas if you consider for 8 units, it can sustain its structure only for a narrow range of field. So though the system is getting energy continuously, its binding energy is increasing, we cannot say that the system is getting structurally favorable. So there is no strong correlation between the energetic stability and the structural stability of the system. Next, we come to homolumo gap. And as we know, homolumo gap is an important index for measuring the chemical stability of the system. So this first plot is for tetramer chain, second is for pentamer, and the third is for hexamer. So if you just check for this, we see here that the homolumo gap with increase in the field, it increases. That means the chemical inertness of the system increases. It reaches the maximum at one particular field, and then it starts to close. So this particular field at which the homolumo gap starts to decrease, we call it as threshold field. So this peculiar behavior of the increase of the opening, or say the closing of homolumo gap, and then again increasing of homolumo gap, and then after some point decreasing of homolumo gap is seen in this system. And this we have tried to understand in terms of redistribution of molecular orbitals. And if you see here, here we have plotted molecular orbital energy versus field. So if you see here for LUMO, what happens is like up to a certain field, the LUMO energy increases, and after one point, with the increase in the field, the LUMO energy almost saturates. So the LUMO, if you see here, the LUMO it migrates slowly migrates towards the other end of the cluster. Whereas at the same field, if you see HOMO, it almost remains constant, by the difference increases, and then after again from this particular field, that is a threshold field, it starts shifting towards the other end, and its energy increases, and thereby again there is the closure of homolumo gap. This is how we account for the peculiar behavior of the increasing and decreasing of homolumo gap. Now, as we saw that there is a particular field value beyond which which marks the onset of the closure of homolumo gap, and this, the more the threshold value, the more the system is chemically stable. So if you see here, we have plotted the threshold field values with respect to the number of units. Here we see that the threshold value for the pentamer chain are is maximum.
Smita, you have 2 minutes.
Yes, sir. Followed by tetramer chain, and the least is for hexamer chain. So as we saw before, the dipole moment was least for pentamer chain, and here we see there's again for the pentamer chain, the threshold value is the highest. So from here we can see that pentamer chain they are more chemically inert in comparison to the other chains. Next we have, and all these calculations were done using our famous functional, that is B3LYP. So we have also tried to do the calculation using two other functionals, which takes care of the dispersion effect with B3L, which is ineffective. So this with the use of these two functionals, we have calculated properties like dipole moment, homolumo gap, and other properties. So here again, we see that there is an increase in the homolumo gap value, and then again it decreases. So here the chain remains the same, although the field value increase. Although the values increases, we see that the chain remains same, and the same goes for dipole moment and other properties. So from our findings, we conclude that shorter chains, shorter water chains, they are robust to a wide range of electric field, whereas the longer chains, they are susceptible to electric field influence, and at higher fields, the system collapses. Next, we saw for the pentamer chains, they have lowest average dipole moment value, and we also saw that the threshold value, field value, is the highest for pentamer chain, which means from here the results suggest that the pentamer chains, they are the most stable clusters, followed by tetramer and hexamer chains. Next, and we saw that the homolumo gap increases and decreases, and but the binding energy just keeps increasing. So there is no strong correlation between the chemical and energetic stability of the system. Also, the system which we have considered, they have large dipole moment, which means this particular feature or this particular large dipole moment parameter, this can be exploited and can be used in nano-based devices, and this particular dipole moment can be modulated by using some electric field. So these are my references. Thank you.
Okay, thank you. Now, any question, please?
Professor Thapa Madhurima here again, and I
yes,
have
please.
a question for Smita.
Yes, ma'am.
I have a comment and a question. The comment is it would have been nice if you had shown us the optimized geometries of all these, because you gave us the initial geometries. There is a certain steric hindrance that happens, and it would be useful to see the output rather than just the input. That was a comment. And the question is the following: did you do just a normal DFT, or did you try doing a time-dependent DFT? Because TDFT works better.
It's just time-independent, normal DFT.
The TDFT works better when you're calculating homolumo, especially with reference to electrical fields. So maybe that will be a good choice to try to refine your results.
Yeah. Okay. I have one question, Smita. Hello.
Yes, sir.
The unit you have taken for electric field, one atomic unit, you have given at the end. Okay. Now, on what basis have you considered that AU? I believe that is atomic unit.
Yes, sir. So whenever we consider this atomic system, we generally don't use volts or volts.
No, I understand that. No, I understand. My question is that on what basis have you taken that unit?
Yes.
You have shown it at the end. You have shown at the end. Can you just go to that?
So I'm disabled.
Okay.
Okay,
In fact, you have some one atomic unit equals some volt angstrom something. My question is on what basis you have chosen that?
Unit in the sense, you mean the magnitude of the electric field? The unit.
No, the numerical values which you have taken.
Okay. Yes,
right?
sir.
On what basis have you taken that?
Yes, sir. Sir, it
that
is
my question.
this particular structures, they are not stable in isolation. Only when we confine it, this particular structures exist. So for this structures to exist, we have to apply some electric field.
No. You just my question is very small. Don't go to this structure. Just on what basis have you taken that atomic unit? One atomic unit equal to something, some numerical value, volt per angstrom you have taken. Is it not, sir? That is only my question. Okay.
Yes, sir. So it is just only you have to take a field value.
Is it given in the code? Is it already used in the code?
Yes, sir. In Gaussian program.
Okay, that's fine. That's fine. Okay, thank you.
With the field, sentence frame is not right with it could be
If there are no other questions, thank you very much, Smita, please.
Very important how to frame sentences.
So we go to the second talk of the sessions by K. Manjunatha. I think it's bismuth doped cobalt chromes nanoparticles, a detailed study of structural, microstructural, electrical, and magnetic properties. So, Mr. K. Manjunatha, you can proceed, please.
Thank you.
Well,
Good afternoon, one and all. I am going to present a detailed study of structural, microstructural, electronic magnetic properties of bismuth doped cobalt chromate nanoparticles. Outline of this my presentation: introduction to cobalt chromate nanoparticles, method of synthesis, characterization, results. Introduction: cobalt chromate nanoparticle belongs to type 2 multiferroic material. Multiferroic means which exhibit more than one of the primary properties such as ferromagnetic, ferroelectric, and ferroelasticity. Multiferroic means which have 2 or more primary ferroic atoms in a single material system. That type of metal can be used in great potential application in various devices such as random access memories, multi-bit memories, data storage, telecommunication system, electromagnetic sensors, etc. Cobalt chromate nanoparticle as a spinal cubic structure, it is having spinal cubic structure and having general formula ABTO4, where A is the divalent metal ions, B is the trivalent metal ions. In this present work, we have systematically synthesized the bismuth doped cobalt chromate nanoparticle to understand the structural, microstructural, optical, DC conductivity, and magnetic behavior of the sample. The flowchart of solution combustion method. The solution combustion method, the stoichiometric amount of metal nitrate such as cobalt nitrate, bismuth nitrate, chromium nitrate, and fuels, as we have taken a mixture of fuels, that is urea and glucose. That taken as oxidizer fuel ratio is 1 because of due to the valence of oxidizer fuel based on valence of oxidizers and fuels. This stoichiometric amount of solution was diluted with a double distilled water, and this solution is mixed through a magnetic stirrer for 1 hour to get a homogeneous solution. This homogeneous solution was preheated, is kept on a preheated open furnace at 450 degrees Celsius for a combustion process. This process will take within 20 minutes. After 20 minutes, we can get a nano size powder. This powder can drain by using water. It's a characterization technique is XRD. It confirms the formation of single phase structure, and also we can calculate the structural parameters of the samples. Scanning electron microscopy to understand the microstructural properties of sample. Transmission electron microscopy to find the particle size of the samples. UV visible diffuse reflectance spectrometer, we can estimate the energy gap of sample. DC conductivity, from this DC conductivity we can calculate the activation energy of the sample. Strict magnetometer to study the magnetic properties of the sample. Results and discussion. This confirms this is the XRD pattern. It was fitted by reticle refinement software. It confirms the single phase formation, and also the index HKL values confirms the spinal cubic structure of the samples. And also from this XRD pattern, we have calculated the crystal size is found to 50 nanometer. Lattice parameter also found to be 8.331 angstrom. Volume also we have calculated. Hopping length also we have calculated from the structure XRD pattern. Scanning electron microscopy, it shows the semi-electron clearly shows the highly porous nature, and also we observe the dry foamy powder due to that's evolution of combustion process. This transmission electron microscopy, 10 micron clearly confirms that particles are agglomeration and also well spherical in nature. This particle size distribution diagram clearly shows that particles are varies from 14 to 32 nanometer, and most of the particles are observed at 22 nanometer. Rings observed in the SAID pattern well indexed, and also it is well matched with the spinal cubic structure. It shows the samples are in well crystalline in nature. This is the UV diffuse reflector spectroscopy. This was started by using Kubelka-Munk relation. That Kubelka-Munk function, f of r is the Kubelka-Munk function, that is 1 minus r whole square, f of r is equal to 1 minus r whole square divided by 2r. From UV diffuse reflector spectroscopy, we have calculated the energy gap of the sample. This is DC conductivity. Here we are, this is the first graph is called the active Arrhenius plot. From Arrhenius plot, we have calculated the energy, activation energy of the sample. Minus EA is equal to minus slope into Boltzmann's constant. The DC conductivity versus temperature graph clearly shows that the temperature increases with conductivity also increases. Temperature dependent susceptibility clearly shows that at high temperature it shows the paramagnetic nature. Whenever temperature decreases, at certain point suddenly the both ZF and FC curve suddenly increases. That region is called the that temperature is the Curie temperature. That place is called the ferromagnetic transition. And at certain point, the both ZFC and FC curve travel in different direction. But FC curve, one certain region, suddenly it is increases. That region is called the conical spiral spin transition. That temperature is called the spiral transition temperature. It is observed around 26 Kelvin. Field dependent magnetization. Here we have measured the MH loop for 300 Kelvin, 95 Kelvin, 25 Kelvin. At 300 Kelvin, we are figure clearly shows that linearity, and also this linearity shows the paramagnetic nature. At 95 Kelvin, the figure clearly shows that MH loop clearly shows the ferromagnetic nature. At 25 Kelvin, MH loop clearly shows with good hysteresis with coercivity and remnant magnetization. Conclusion: this mode of cobalt was synthesized by solution combustion method using mixture of fuels such as urea and glucose for the first time. XRD pattern reveals the formation of single phase with spinous cubic structure having space group FD3M, and also crystallized size is found to be nano size and lattice parameter is found to be 8.331 angstrom. Same micrograph shows the highly porous nature. TEM images confirms the particles are almost spherical in nature and agglomeration, and these results are the particle size results are very well matched with the XRD results. The particle size is varied from 14 nanometer to 32 nanometer. Most of the particles are occurred at 22 nanometer. Rings observed in the SAD patterns are indexed, and these indexed HKL values are well matched with the spinal cubic phase of cobalt chromate. This confirms the synthesized material is well crystalline in nature. The energy gap is found to be 2.7 electron volt. The activation energy is found to be 0.74 electron volt. The temperature difference susceptibility of the cobalt chromate nanoparticle clearly shows that the two transition, that is ferromagnetic transition, and one more is conical spiral transition. It clearly visible at critical temperature, that is 98 Kelvin, and spiral transition phase occurred at 26 Kelvin. These both are occurred at the susceptibility, FC susceptibility, the MH loop. It clearly shows that at 300 Kelvin, the sample shows a paramagnetic nature, and at 95 Kelvin, it shows a ferromagnetic nature, and 25 Kelvin, it shows a clear hysteresis loop with coercivity and remnant magnetization. These type of samples we can use in great potential application for electromagnetic sensor and random access memories, etc. Thank you for giving this opportunity, sir.
Okay, you're just in time. So any question, please? Well, Mr. Manjunathan, I have one question, okay? Now, you have shown that susceptibility versus temperature plot. Now, there you have just, this is the one. There you have just taken the field at 100 oyster only. What is the reason there? What is the reason?
Sir, actually, I am working in Presidency University, Bangalore, sir. We have only one center in Bangalore, sir. IISc Bangalore, and one more is JNCS Bangalore. They have charged for that MH loop and all. They have charged, sir, like one per sample 6,000. That's why my supervisor advised only for 100 oysters, sir, because we have so many samples. That's why he has only told like.
No, this particular field, can it be changed in that experimental setup?
No, sir. We have only, sir. We have measured at 500 oysters also. It has not, same. We can observe same field only, same temperature only. We can observe ferromagnetic nature. We can observe spiral transition temperature, same only, same place.
I see. Okay.
Field increases also. We can occur same transition.
I see. I got it. Okay. Thank you so much. Any other question, please?
Yes, sir. I have a question, sir.
Yes.
Hi, Manjunatha.
Thank you.
It was a really interesting talk.
Yeah.
I would like to know if the energy gap that you are talking about is same thing as the band gap that we talk in solid state physics. Did you get my question?
No, ma'am. Can you explain, please?
The energy gap that you are talking about, is it the band gap?
Yes, ma'am. It is band gap only.
And also, can you explain what the activation energy actually is?
The activation energy is 0.74 electron volt, ma'am. This was started by using Arrhenius equation. That is,
I want to know what is activation energy. I don't want to know about
means samples can. It is required for activate the samples. how much energy is required for activate the particular sample. That is called activation.
Activate means?
For a suppose we have to give some energy for such material. Electrons are jumped from valence band to conduction band.
Oh, so the required energy, activation energy.
Yeah. Yes, ma'am.
Okay. Thank you.
Thank you.
Okay, Mr. K. Manjunathan, thank you very much.
Thank you, sir. Thank you, sir.
Okay, now we have.
Excuse me, sir.
Sorry?
Sir, I am Pragya Singh. Hello.
Yes.
I
Yes,
have
please.
I also have a question.
Yeah, please go ahead. Go ahead, please.
Mr. Manjunathan, I actually have two questions. My first question is, how do you explain the multiferroic behavior in cobalt chromite? And my second question is, where you have shown the ZFC and FC curve, there is a bifurcation around 90 Kelvin. What does that bifurcation mean?
Not bifurcation. Suddenly it is increasing at 98 Kelvin. Actually, samples are in paramagnetic nature at high temperature. Whenever temperature decreases, suddenly it is increases. Both ZFC and FC curve suddenly increases. That reason is called the ferrimagnetic nature. That temperature is called the ferrimagnetic
generally,
zero temperature.
Yeah, but generally this bifurcation is related to superparamagnetism or spin glass like behavior.
Bifurcation, it is occurred after blacking temperature only in our sample.
Yeah, so how do you explain that bifurcation for your case?
Bifurcation actually in antiferromagnetic nature only, I know, ma'am, that bifurcation after blacking temperature only, in that FC field only we are taken to measure to conical spiral spin transition. FC curve. Field cool. Second thing is cobalt chromate is it is a type 2 multiferroic material, ma'am. Now we are doing the low temperature dielectric properties also. We are going to combine with dielectric, that is dielectric constant versus temperature dependent dielectric and field dependent magnetization. Now we are doing, ma'am, actually that only one sample only we did. We got the spiral transition temperature at 25 Kelvin. You both using dielectric studies as well as magnetic studies, ma'am. In IISc Bangalore, MRC lab only we have done, ma'am.
Actually, my question is, multiferroic behavior means presence of more than one ferroic order. For example, ferroelectricity and ferromagnetic ordering, something like that.
Yes.
So, how do you achieve these two types of ordering in cobalt chromite?
Because cobalt chromate is type 2 multiferroic. Type 2 means that ferroelectric order and ferromagnetic order is occurred in same origin. So we have done dielectric studies, same temperature, and that magnetic studies in same temperature, like 2 Kelvin to 300 Kelvin. Like we have done both measurement, ma'am. We have observed small anomaly at dielectric measurement also. So it shows a ferroelectric nature by using dielectric studies. One more, ferromagnetic is occurred by using magnetic studies. So these two transitions occurred at same temperature in a single material, both ferroelectric and ferromagnetic. So multiferroic means it exhibits two or more primary properties like ferroelectric and ferromagnetic. These two orders are occurred in the same origin, ma'am. In this cobalt chromate nanoparticles, we have done the measurement also, ma'am. IISc Bangalore.
Okay, thank you.
Thank you.
Thank you so much. Thank you very much.
Thank you, sir. Thank you.
Now we move on to the third presentation, third and the last presentations of these technical sessions. This is by Mr. Bishnu Karki from Tribhuvan University, and the title of his presentation is Novel Topological Wile Semi-Metallic Phase in Layered Material Fe2SN. Mr. Karki, please.
Thank you, sir.
Welcome.
Well, good afternoon. I'm Bishnu Karki from Central Department of Physics, Tribhuvan University, Nepal. Now I'm presenting my recent research work on topological materials conducted under the supervision of Dr. Madhav Prasad Gimire. The topic for today's talk is novel topological wile semi-metallic phase in layered material Fe2SN. These are the contents or the plan of today's talk. Basically, I'll be introducing the topic, talking about some methods, and then move towards the result in our system. Talking basic, what is topology? Topology is the concept developed from mathematics which says the certain properties of the system remains invariant under the action of deformities. For example, a do not is topological, you can see here, a do not is topological equivalent to a coffee cup. Means both have same number of holes. And 2i is topologically equivalent to a sphere since both have no holes. Means both are topologically equivalent. And other examples also we have, like as this tribal knot, this Mobius strip. And this topology was mathematically explained by Gauss-Bonnet theorem, in which the theorem states the integration of the curvature over whole area always gives a constant number, that is genus value G. As we can see, genus value for the cup and donut is 1, and genus value for the sphere is 0. That genus value is given by the curvature or integration of the curvature. Nowadays, topology has become a multidisciplinary approach, and in the case of physics, we have topological materials. We use topological algebra to explain their properties. For example, we have topological insulators, in which only the surface is conducting and the bulk part is insulating. We have other materials like as condo insulators, we have topological superconductors, and we have topological semi-metals. And our major interest is this topological semi-metals. Our topological semi-metals are mainly of two types, Dirac semi-metals and Weil semi-metals. And I'm currently working in this Weil semi-metals part, and now my further slides will be mostly on the Weil semi-metals. Now the question arises, why to study topology? For this, we have to know the drawbacks of present day technology. Our present day technology is based on electronics, that is in the form of binary digit, that transfer information in the form of binary digit through electrons. And our laptops, our mobiles get heated, they lost a lot amount of energy in the form of heat. And if that can be corrected, then we have the solution. That solution is through if we can create a topological device that is only the surface state is conducting and the bulk part is insulating, then the lot amount of heat energy can be saved. Moreover, we have Fermi arc transport phenomenon in topological devices also. Fermi arc transport phenomenon that is very much faster, even around the speed of light, faster transport phenomenon. Also the topology can be used in quantum bit. So these topological devices can be the probable future application or future advancement of the present day technology. And now the first mathematical credit for this semi-metallic state goes to the two renowned scientists, Paul A.M. Dirac and Armand Weil. Paul Dirac first formulated the Dirac equation, which is a 4x4 matrix equation, and the solution of that matrix equation gives a Dirac point, and the Dirac point is the source of Dirac fermions. And Armand Weil, after a year later of Dirac, he solved that Dirac equation, putting the mass, setting the mass to 0. Then he get the two-folded points known as Weil points, and the Weil points are massless but charged quasi-particles, and those states are known as Weil fermions in the particle physics and Weil state in the solid state physics. Now, realizing the Weil fermions or Weil states in the solids, we have Weil semi-metals. In case of Weil semi-metals, we have in the band structure, we have valence band and conduction band crossing each other at certain nearby the Fermi level, like as shown here. And this point is known as, if they crosses at the nearby the Fermi level, that point is known as Weil point. And the Weil point is mainly created if the system breaks the time reversal symmetry or inversion symmetry or both. If that is going to break both or either of them, then there is the creation of Weil state in that system. And if we go for the properties of the Weil nodes or this point, this mainly follows Weil equation. It is a source of the magnetic monopole and creates a magnetic field known as Berry curvature. And two Weil nodes are mainly connected by the Fermi arc states. And more other properties of Weil semi-metals are they have high mobilities, they have magnetotransport phenomenon, they have large magnetoresistance. Mainly there are two types of Weil semi-metals recorded till now on the basis of cone. You can see in the figure also, and our previous speaker in the previous session also explained about this. Now, what methods we mainly applied computational approach approach for the calculation, we use FPLO code, that is full potential local orbital code, for the DFT calculation. And through that DFT calculation, we predict the electronic and magnetic behavior of system. Then through the one-air interpolation approach and very phase formalism approach, we move towards the topological behavior of the system. And in the topological behavior, we calculate the wild properties of the system. We calculate the Chern numbers of that wild points, and also calculate the anomalous Hall effects in that system. And now I'm moving towards my results in this layered material, that is Fe2SN. Simply, it's a hexagonal material, and it's layered formed by iron, one layer formed by iron, and next layer formed by iron and tin, and this continues to form a layered material. And this is a mainly this is space group number 164 with P63 by MMC symbol. And main thing to notice here is it is a non-symmetric system. If a system is non-symmetric, then it is going to break the inversion symmetry, and that is the basic criteria for the Weil-Sim metals. From here, from this crystal structure, we can know this can be the probable candidate, since it breaks the inversion symmetry, and it is a probable candidate for the Weil-Sim metals. Here, the down one figure is for the isometry points that is chosen in the band structure. Now the magnetic, talking about magnetic effects in the system, among the possible magnetic configurations, antiferromagnetic configuration and ferromagnetic configuration, we find that the system is ferromagnetically stable at the ground state. And if the system is ferromagnetically stable, then ferromagnetically stable, or if there is some magnetic moment in that system, then it is going to break the time reversal symmetry. And if and next criteria is for the Weil-Sim metals also fulfilled, that is it is going to break the time reversal symmetry, since it is a ferromagnetic system. Now talking about the electronic band structures in our system, we applied both, we calculate the band structure with by applying SOC in two directions, that is 100 and 001, that is along x-axis and z-axis. And also without including SOC, we calculate the band structure, and we can see there the SOC effects, since there is tin is present in that system, and tin is a heavy metal, heavy element in elements. So SOC effects are clearly seen around this isometry, like as we can hear, the bands are opening, and in many other regions also we can see the SOC effect. And also directional effect is also present in the system. That is, we can see the band this blue band and red band. This is the SOC applied along the x-axis, and the next band is SOC applied on the z-axis. The bands are opening. For example, along K gamma region, we can see the bands are opening. That is, there is some directional effects in SOC also, and this can be proved by the there is the energy difference between the two directions, that is around 0.95 MeV. So there is magnetic anisotropic effects also in the system. And the blue band and the red bands are crossing at various points nearby the Fermi level. So these bands are a matter of interest for the Weil calculations and Weil point searching. Now looking towards the density of the states, we mainly find iron 3D states and tin 5P states around the Fermi level. As we can see here, iron 3D is contributing more, and SN5P is contributing less, but it is contributing, though less, but it is contributing. So taking these local orbitals, iron 3D and SN5P, we did 1 year fit, and generated 1 year Hamiltonian. 1 year fit is mainly the matching of bands, that is that we calculate from DFT, and that by using 1 year function and by using tight binding approximation. Then we generate 1 year Hamiltonian. After generation of 1 year Hamiltonian, using very curvature formalism, we check whether there is the wild points are real wild points or not. Then along 001 axis and along 100 axis, we found the wild points with various energy ranges. We can see here the 6 energy ranges of wild points are found in 001 axis, and along 100 axis we find 7 energy ranges of wild points with definite chirality, that is ±1. And also these wild points have, there are many even copies of them. They are conducted by the symmetry operations. I have not, due to less evaluative time, I have not included them here. Now talking towards the anomalous Hall effects in the system, simply anomalous Hall effect is the integration of this Berry curvature value, that is the magnetic field value, Berry curvature along the Brillouin zone multiplied by the occupation factor. Here we find the peak values around this energy range. peak values for the anomalous Hall effect. Means the system is breaking time reversal. Those systems that breaks time reversal are the good anomalous Hall effect, all effects device, all effects systems. So our system is also a good or probable candidate for the anomalous Hall devices in the future, since we have high anomalous Hall effects in the various season, and this is due to the presence of wild points. Since they are the source for the magnetic field known as Berry curvature, and they have the Berry curvature value is high, so we get the high values of this anomalous Hall, that is sigma x anomalous Hall conductivity sigma xy around this energy region where the wild points we identify the wild points. Now, moving towards the conclusion of the work, finally we concluded that the Fe2SN is a layered material and it's a ferromagnetic ground state. Also, there is associated effects in the system. And since the system breaks both time reversal and inversion symmetry,
Well, Mr. Turkey, your time is up.
And it's wild same metals, and there is high peak values of anomalous Hall effect, and it is a good anomalous Hall device. Finally, I'd like to acknowledge IFW Dresden and PD Manual Director for their support for the legalized software of FPLU and computational supercomputer facilities. Finally, thank you.
Thank you, Mr. Karki. Any questions, please? Well, if there is no question, then I just would like to ask you one thing, Mr. Karki. You have shown in the very first slide,
yes,
you have shown that equation equal to 2 minus 2z, all right?
Yes. Yes,
What is
sir.
that z stands for?
Z is the genus value. For example, if in any system, if there are number of holes is 0,
right?
0, then the genus value is 0. And if any the curvature don't have any holes, that means that is a mathematical concept. Curvature don't have any holes. If for example in a coffee cup and donut, if we just integrate the curvature, then we are going to get the genus value to be 1.
Okay.
I have one question, please.
Yes, please, go ahead.
Yes, Mr. Kage.
Yes, sir.
What is the daily life use of such materials? Can you please?
These are the proposed material for the future day science.
Yeah.
Now, till now, we don't have any topological devices till now, but they are in process. They are I think in the upcoming 50 years, they are going to replace the electronics by wildtronics or topological devices. Since they are very much faster and they lose heat they do not create heat, means they are saving a lot amount of energy. So that's why these devices are the future day science or future day technology, you can say in that way.
Okay, thank you very much.
Thank
you. Okay. If there are no more questions, thank you so much for all your presentations.
Actually, hello.
Hello. Yes, please.
Sir, I'd like to ask one question.
Yes, please go ahead.
In the slide, I saw that the topological concepts have been used in the development of quantum bits. So although it isn't within the scope of the paper, can we please have the speaker shed some light on it?
Yeah, Mr. Karki, can you just highlight something on this one, please?
Yes, we have.
Yeah.
Yes, till now we are the scientists are in process of working in the system. We have Marona states that are found in the age region of this Weil or Dirac states, and they are directly applicable for the quantum states. They have explained in that way. Just mathematically, it's mathematically they have explained in that way, but till now the applications has not been formulated. Okay. It's still in process.
Okay.
All right.
Well, that was it. Thank you.
Okay, thank you.
All right, thank you very much, please. Dr. Amit?
Sir, he's not here. He's in another. Okay, he's here.
Okay.
Okay, very good afternoon. Thank you, Professor R.K. Thapa, for nicely and tactfully handling coordinating all this station. and managing the session, right? And thank you, speakers, the participants, for your nice presentations and for sharing your recent advances or the recent works that you are conducting in your respective laboratories. And recently, Mr. Karki said that these materials are under process and they may find the application after 50 years, like NICE slate. Now, because we are continuously developing in the electronics and other fields, but slowly this development is now going flat. So with this flattening nature of our development, we need to have extra supportings, or we need to find something extra that will boost our development further. So with this, we hope that these sort of the materials will find a better opportunity for our next coming futures. And with this, we are concluding this oral presentations and for day one. And once again, I would like to thank Professor Arkithapa and the participants and the oral presentation, and also the participants who are listening to the lectures and without whom all the sessions are not possible. And we are ending the sessions, and one more announcement. We will meet at 7 p.m. Today, 7 p.m. this evening. And the link for the next session will be shared to you in the WhatsApp group. And tentatively in the WhatsApp group, it's not possible to send everyone through the email. And it seems some people are not checking the emails properly. So it will be communicated in the WhatsApp group. Please kindly join there. See you at 7 p.m. Okay. And at 7 p.m., let me just a brief idea. At 7 p.m., we have the lectures, invited lectures from Dr. Randu Gupta from Israel. And after that, we have the, Professor P. Paulus, IIT Guwahati, but since he is now in USA, so his lectures have been scheduled this evening. And after that, we have the Dr. Erlis from Argentina, and followed by Dr. P. Pradhan from MIT USA. So these are the highlights of the evening session. So we will meet you in the evening. With this, we are ending this morning session here. Thank you very much to everyone, the participants and the speakers, and the coordinator of the session. Thank you very much. Have a good day. We are ending. Thank you.